Hi, Frankie. We do all sorts of things for fun. We like to look out the window and look back out at the Earth. We do things like play with water, like we showed you earlier. We read books. We call home and talk to our families. And we just hang out together. We kind of have our own little space family up here, so we're always spending time with each other when we have time off.
Hi.
Another thing, actually, Mark's going to show you. Oh, sorry. Another thing Mark was going to show you is we actually have some musical instruments up here. And I think that maybe is the next question, which is Mark's telling me. But we have a guitar and a piano, and maybe we'll let you cut to the next question, then we'll show you our guitar.
Hi, my name is Calder, and my question is, how does bacteria behave differently in space? Thank you.
Save it.
Bacteria is different on the space station. In fact, there's some strands of bacteria that, like Salmonella, that are actually more strong. So it's very important for us to continue to study those.
Hello, my name is Tennessee. My question is, do you have any musical instruments in space? If so, how do you play them and what do you play?
Now we got the right answer for you, Tennessee. Mark's showing you one of the guitars we have aboard the International Space Station. We also have a keyboard, an electronic piano, and there was a saxophone up here for a while when Thomas Pesquet was here. Unfortunately, I personally don't have much musical talent, so I haven't played any of these instruments with much success. But a few of my crewmates do, and occasionally they'll bust out some tunes for us and we'll have a little sing-along.
Hello, my name is Alexander Connolly, and my question is, what is your job on the International Space Station?
Kayla and I both are flight engineers. I'd like to describe us as laboratory technicians. So every day we're maintaining the laboratory as well as helping out with the experiments. So we facilitate the scientists on the ground accomplishing their science objectives.
Hi, my name is Audrey. My question is, can humans colonize and live on Mars? If so, when do you think it will happen?
Hi, Audrey. I definitely think humans can live on Mars, and that's actually a goal of NASA, to push on to Mars and send human beings there to live and work. So for us, I think the near term, we're going to return to the moon, like I mentioned earlier, and learn how to live and work there much closer to home. It's further than I've ever imagined going in my life, but definitely a lot closer than Mars. So there's an opportunity to get more supplies from Earth and also have less of a communication delay and more support from the ground while we're learning how to do those things, how to drive around in rovers, how to get power, how to use resources, and then eventually we'll go to Mars. I think hopefully sometime in the 2030s, if you're applying to be an astronaut, we'll already be there.
Hi, my name is Langston Mitchell, and my question is, what animals do you have at the International Space Station now?
Langston, we actually have mice on the space station right now. In fact, I had the joy of getting to clean out their habitats this weekend, or maybe Friday. So we make sure we take good care of them up here.
Hi, my name is Emma Westheimer, and my question is, if you have been to the International Space Station before, how did it feel physically when you returned back to Earth?
This is my very first trip to the International Space Station, so I don't know quite how I'll feel when I return to Earth, but I might ask Mark the same question. He's been up here before, and this time he's going to be up here for a whole year before he goes home. So Mark, do you want to talk a little bit how you adjusted last time?
Sure, it's a slow process. I definitely remember feeling sore. You can't fall down on the space station, so there's a lot of balancing that you don't have to worry about. And so I think some of those smaller muscles that we used to balance get a little weak, even though we exercise a lot to work the major muscles. So tying my shoes and bending over on one foot was really hard for me at first. Sitting up in bed even, it was a little challenging. But we adapt quickly as human beings, and I got back to normal before I launched, and it'll go through the process again.
Hi, my name is Lillian. My question for you is, what is the most interesting thing that happened to you in space that you did not expect?
You know, I've spent a lot of time up here, and I didn't think I'd be surprised by anything. But recently, I was just looking out the window at the ground, and most of the time, we're focused on what location we're looking at, and it looks very two-dimensional. But I noticed as I just kind of looked broadly that I could actually see that the things that were closer to me, the tops of very high clouds, were moving at a different rate because the orientation of my view compared to them was changing. It's called parallax. So it was really interesting seeing that there really is some height differentiation that you can observe from the space station, even though it's all very far away from us.
My name is Kate, and my question is, when the capsule detaches from the rocket, how does it feel?
It's one of the more exciting parts of a space flight, I think, because it's when you get to experience zero-G for the first time, the feeling that you're weightless. And so for us on Falcon 9, which is the rocket we launched on, there's kind of two really exciting moments. The moment when the first stage cuts off and the second stage is about to light. And so you decelerate, so all of a sudden you get thrown forward into your restraints, kind of like your seatbelt. And then the second stage lights and throws you back into your seat again. And so that's kind of an exciting moment. And then when the capsule detaches from the second stage, you're in orbit, you're in free flight. And that's when you recognize, wow, I'm in space, we finally made it. And that's actually why we have these things called zero-G indicators. We brought the Crew 3 one to the call today, but this is our turtle. And her name is Fow, but we basically had her in the capsule with us so that when we got to that moment and she floated up, we knew for sure we'd made it.
Hello, my name is Neve, and my question is, do the plants grown on the International Space Station taste different than the plants grown on Earth?
My understanding is that the hatch chili peppers that we tried out were actually spicier than they are on the ground. Now, I haven't had experience with hatch chilies on the ground. Even though they were very spicy, I definitely am going to try them when I get back on the ground. So, yes, first reports are that there are differences.
I'm Morgan Madani, 6th grade student at the Center for Early Education. Thank you for joining us today. Thank you especially to NASA and the crew of Expedition 66. We're excited to follow along as you continue your important work on the International Space Station and wish you all the best. Thank you, and have a great day.
Station, this is Houston ACR. That concludes the event.
Thank you to all the participants. Station, we are now resuming operational audio communications.
But the attack didn't come from the outside. Massive wartime production facilities, a high increase in population, and the exhaust fumes of cars, combined with the geography of the valley, made the city a trap for air pollution. The day after the first event, city officials tried to control the damage by restricting emissions from power plants and industry. But while these efforts helped reduce air pollution, smog episodes continue to occur. Scientists discovered that volatile compounds, like the gases produced due to evaporation of gasoline during the refining process, and nitrogen oxides generated during the combustion inside car engines, both reacted with sunlight, creating a highly toxic gas, ozone. And sunlight isn't precisely something Southern California lacks. But this wasn't a localized phenomenon. Other U.S. cities also experienced high ozone concentration levels. These cases made society aware of the importance of keeping track of emissions and lead politicians to implement policies to improve the quality of the air we all breathe.
Air quality is a serious global problem. More than 7 million people die per year due to the effects of air quality.
There's many economies around the world that are growing, and what the United States has seen is that your economy can still grow while your air pollution levels are decreasing, but it takes some effort to do that. The good news is that air pollution levels around the world are gradually decreasing.
In fact, air quality trends have improved in the last decade as a result of policies developed to reduce air pollution.
Back in the 1950s, Los Angeles had a really awful air quality problem.
So when the Clean Air Act began, it was a commitment to cleaning up the air. But the actual legislation and the differences took a long time to put into place. And so here in Asia, we're at the beginning of that process.
These nations that are still increasing in their standard of living and increasing in their pollution levels can learn from what's happened in the industrialized nations. We can have a more rapid decrease in pollution levels.
Now we know how to put together effective policies to control air quality.
Understanding that economic growth and industrial development bring air quality problems and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
Chorus AQ is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
The Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem from the past decades.
Joint venture with NASA has provided us with many research opportunities.
The air in our planet does not know of national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
Chorus AQ combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that the pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's three key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent from the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants, nitrogen oxides and reactive important in the formation of ozone.
Your car emits both NOx and hydrocarbons are unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas, where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources, and so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forests and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the fourth largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improving air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab, measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA, but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The CHORUS AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the CHORUS AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
CHORUS AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the CHORUS AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
There's one thing that us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today, and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chelmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is IceCat. It's been very quiet, very difficult to launch.
Do you think we're going to launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
You just watched the trailer to the inaugural season of NASA Explorer's Cryosphere. The 9-episode series first launched in October 2018, taking a hard look at the great lengths NASA goes to study a part of the Earth that's often called the canary in the coal mine, a serious indicator of present, past, and future climate change. The show was filmed right here at our studios at Goddard Space Flight Center, as well as on location in California, Alaska, Greenland, Iceland, Antarctica, and the Arctic. Our crew followed many of the people you're about to meet into the harsh elements to capture their stories and were rewarded with breathtaking icescapes. When you think of a NASA explorer, you might imagine an astronaut or even a scientist studying the outer reaches of deep space. In reality, while NASA is unlocking the mysteries of our solar system, it's also looking for answers on Earth, the only planet we know of so far with life. So sit back and enjoy this 9-part adventure story filled with awe, triumph, loss, and courage. Be sure to stick around afterward for even more exciting bonus material from the 2018 Cryosphere field season.
Here at the end of the Earth, it still feels like a place for raw exploration and adventure. It's vast in all directions and ground zero for some of the biggest questions we have about the climate. But when we decided to make a series about the frozen places on Earth, we knew there would be one hurdle we would need to jump over first.
What is the cryosphere?
The what?
Ooh.
I have no idea.
While I'm aware of the cryosphere, I don't actually know what it is.
It has something to do with ice. All right, that's all I got.
How do you get people acquainted with the cryosphere when most of us don't even know what it is?
Hey, so here we are in Washington, D.C., standing on the roof of NASA headquarters. That's the Capitol building right behind me. And what headquarters does is kind of serve as the focal point to connect the dots.
That's Dr. Tom Wagner, NASA's cryospheric program scientist at headquarters. In short, Tom is responsible for making sure NASA knows what the current status of the cryosphere is.
The cryosphere is everything from the snow that falls by your house to the icy reaches of the Himalayas, to the big ice sheets of Antarctica all the way at the South Pole, and also the frozen ground of the Arctic, and even some of that frozen ground that's currently under the ocean.
If you had to break it down, you'd have a mix of sea ice, snow cover, permafrost, ice sheets, and glaciers.
Right now, our best predictions are that sea levels will rise anywhere from 1 to 3 feet within the next 100 years. 3 feet of sea level rise has the potential to displace about 100 million people, which is a lot of people that need to find new homes.
Our current reality places us at a near tipping point, and the cryosphere is playing a huge part in that delicate balance.
So one of the things people don't know about NASA is that we study the Earth, and we've been doing that since NASA's inception back in the 1950s. And we study the frozen part of the Earth in a variety of ways.
Missions like SNOW-X, Airborne Snow Observatory, Oceans Melting Greenland, Operation Icebridge, Arctic Boreal Vulnerability Experiment, and countless other labs and individual researchers stand at the forefront of monitoring the cryosphere. But this year was a particularly big year.
3, 2, 1, and liftoff of GRACE follow-on, continuing the legacy of the GRACE mission of tracking the movement of water across our planet.
2 state-of-the-art satellite missions are being launched in a single year as part of a major attempt to understand Earth's frozen places. Our scientists are answering hard questions, sharing stories from the field, and giving their best predictions for what we can expect of a warming world. We're taking you with us as we follow NASA explorers on their journey to the frozen ends of the Earth as they study our rapidly changing world from satellites, planes, and boots on the ground. What we think of snow depends a lot on where it falls. If you live in the eastern US, maybe it's fun. Or maybe it's just a pain.
But if you live in parts of the world where they depend on the water that's in the snow for a large fraction of their total water that they use for drinking, for agriculture, for industry, or for hydropower, the snow is a very important natural resource. For example, in the western part of the United States, 80 to 90% of their renewable water comes from snow.
Snow is one part of the cryosphere that many of us have actually encountered before, but it also plays a critical role in regulating the Earth's climate. Through decades of remote sensing, NASA has kept a close eye on the ebb and flow of snow cover.
We now have a 52-year record of snow cover in the Northern Hemisphere, and we can see changes in the extent of snow cover over the time period, particularly in the last few decades, where we can see that the snow cover has been retreating. It's been melting a lot earlier in the springtime.
The extent is relatively easy to do, and it has been done over the years. What's tricky is, though, how thick is that snow? And it's even trickier how much water is in that snow.
That tricky part is known as the snow-water equivalent, or how much water would actually be in a layer of snow if it melted. NASA and its partners have taken to the air to help solve this elusive mystery. First, there's the Airborne Snow Observatory, or ASO, a small plane outfitted with a couple of instruments, one of which measures snow depth using LiDAR. LiDAR measures distance using light from lasers. Since 2014, ASO has flown over basins in California and Colorado, taking before and after looks at snow depth. Scientists subtract the snow-free summer data from the snow-on winter data to get an idea of the snow depth. There's no single way to measure all types of snow across the globe, and so NASA's other airborne campaign, SNOWX, is testing different combinations of sensors. This winter, SNOWX will test a new instrument, the Snow-Water Equivalent Synthetic Aperture Radar and Radiometer, or SWISAR.
SWISAR consists of two main components, one of them being the radar and the second one being the radiometer.
So with the radar providing the depth of the snow and the radiometer providing the density of the snow, we could put those two things together and get the snow water equivalent. Here in the chamber, we're going to measure different radiation patterns at our different frequencies and do some full system testing in this chamber. This chamber kind of enables us to isolate various types of radiation and interference. And in about a month, we're going to take the instrument, mount it on a Twin Otter in the Grand Mesa in Colorado, and we're going to fly it over the Grand Mesa and take various different measurements. This is what we call our engineering flight.
Making sure the sensors are calibrated is key in order to face the challenges nature will throw at them.
Half of the area that gets covered by snow every winter contains trees and forest. And the trees make it difficult for the sensors to see the snow that's underneath the trees, so it makes it difficult for us to measure how much snow there is. After the snow's had a chance to sit on the ground for a while, it gets denser and denser and denser over time, and it changes, which is another reason why snow is very challenging to remotely sense. It doesn't stay the same. It's constantly changing. One of the things that we often do in the field is go dig what we call a snow pit. We literally dig a pit in the snow so we can see all the different layers. The layering is very important.
All this digging is part of ground truthing SNOWX, a way of matching up what the airborne instruments see and what is actually sitting on the surface. The ultimate goal of SNOWX is to figure out what the best combination of instruments would be for a future satellite mission in order to get a global picture of snow.
We need to know how much snow is in a snowpack, because if we have too much snow and the snow melts too fast, then you can get flooding. And if you don't have enough snow, or if the snow melts too early, that can lead to a longer wildfire season, a more intense drought, and we need to know these things for water resource planning.
I can't really name anyone that has so much integrity as she does to the things that she's accomplishing. It's pretty amazing. Having Claire as a role model, just a strong woman in science and just so smart and so kind. It's just a huge confidence booster. Is that, hey, I could do that too, you know? That's possible, that's successful, that's what I want to do.
I would characterize her as a pioneer in the field.
The amount and quality of the work she's put out is second to none.
I know people who have a lot of tenacity. I know people that have integrity, but it's rare that people have both together in that, you know, that combination that Claire does.
Every morning, Dr. Claire Parkinson gets up before sunrise and runs 2 miles to work. She hasn't missed a day in nearly 40 years. To know the evolution of sea ice and how we observe it from space is to know Claire. This year, she's celebrating 40 years at NASA.
When I arrived at Goddard, which was in July of 1978, it was an incredibly exciting period here. Satellites were pretty new, but a lot of data had been collected.
NASA scientists were inundated with information, and Claire was in a cohort looking at sea ice, trying to make sense of a jumble of very raw, very new data. It was around that time that Claire and her team, at the time led by Dr. Jay Zwally, created the principal sea ice record that we use today.
How does something like that record help you do your job?
Oh, that record is fundamental to understanding sea ice. So without it, we wouldn't know how rapidly it's changing.
You may not realize it, but Claire's work studying the changing extent of the ice caps deeply affected our understanding of climate change, and relatedly, our understanding of how climate change affects life on Earth.
One of the clearest signals for climate change that resonates with people has been this shrinking of the polar ice cap in the summer that we're able to see because of Claire's work.
After we had a record that was about 15-20 years long, we started noticing that the extent of the ice in the Arctic was getting smaller over time.
Sea ice is formed on the surface of the ocean, and therefore is made from seawater. The biggest concentration is in the Arctic, and it's also where the biggest loss in sea ice is occurring. Every year, NASA reports on the sea ice minimum and maximum extents. As expected, the data is concerning.
By now, not only has this trend toward lesser ice continued, but it's even accelerated, so that now the decreases are greater than what they had been.
These trends are deeply troubling, but one thing's for sure. Our awareness of shrinking sea ice extent due to climate change was propelled faster and further after Claire Parkinson arrived at NASA.
I mean, she takes her job seriously, and the health and welfare of those instruments in space, yeah, she's on it. You know, it's one of the things you don't worry about because Claire's in the loop on these things. It's going to be fine.
In science, we stand on the shoulders of giants, on the shoulders of those who explored before us. But then, some among us are giants.
Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's climate. Oh, that's the climate you got. You take a bunch of weather and you average it together and you're doing the climate rock.
Glacial pace. It means something's happening so slowly you can barely tell it's happening at all. That used to describe the very incremental movement glaciers and ice sheets experienced each year. But now that's changing. We're tagging along with 3 NASA scientists to understand the different lengths they go to not only investigate ice sheets and glaciers, but also communicate their often complicated science to the public. First, let's get oriented. Ice sheets, in pink, pretty much occur in only two places: Antarctica and Greenland. Glaciers, in yellow, play a key role draining melt off the ice sheet. Glaciers are also found in the high mountains, but we'll get to those in another episode.
So we know that something's happening in Greenland right now that's unprecedented in the last several thousand years.
That's Dr. Josh Willis, oceanographer at the Jet Propulsion Laboratory. Josh and his team are tackling one of the major environmental challenges of the 21st century, trying to answer fundamental questions about how melting glaciers impact sea level rise.
With my mission, Oceans Melting Greenland, or OMG for short, we're trying to understand just how much of Greenland's melt is caused by the oceans.
Along with being one of NASA's top scientists working on the cryosphere, Josh is passionate about demystifying climate change in typically unconventional ways.
I think by reaching out to people with a little bit of humor, a little bit of fun, maybe a song, you really have the opportunity to help people understand and come to terms with what we're doing to our planet. Because it's definitely happening and it's definitely a big deal, and we need to start preparing for it.
Down at the opposite pole, Dr. Kelly Brunt is getting ready for a major expedition.
In December and January this coming year, I'll actually be in Antarctica, down near the South Pole, collecting ground-based GPS data.
This is actually Kelly's second expedition to the South Pole. The first occurred in December and January of last year. Both surveys are critical and will help validate data collected by NASA's airborne campaign, Operation Icebridge, and the recently launched satellite mission ISAT-2.
All three of these layers, that ground-based, that airborne, and the satellite, are all tied together. The ground-based helps validate both the satellite and the airborne airborne helps give us more validation data for the satellites, but also a bigger story with respect to the depth of the ice sheet and what's going on underneath the surface.
While some scientists are taking measurements in the field, others are looking for answers in physics and lines of code.
For me, those projections that we are doing, they do have a very personal meaning.
Dr. Sophie Nowicki is an ice sheet modeler. That means she and her team have the important job of forecasting how ice will change in the future, which also predicts changes in sea level rise. It's a job she doesn't take lightly, especially since urban planning and infrastructure use her team's models to make decisions about the future and safety of their communities.
When we make those projections that are 100 years in the future, 100 years can seem so far away, like I don't have to worry about it, it's just too far. But actually they are not. It's really like the future that we are looking at that our children or grandchildren will see to experience.
Whether it's learning to communicate in new ways, traversing a swath of Antarctica in a massive piston bully, or taking responsibility for an impactful climate forecast, our NASA explorers are pushing the limits of discovery every day. But on a very human level, they're people with families and friends who have a stake in finding out why and how the planet is changing as rapidly as it is.
Some places on the surface you might have these steep cracks and giant fissures that you would have to be careful not to fall into. In other places you might see towers of ice right next to places that were relatively smooth. You might see places that were dark. Ice there takes the form of rock. It's frozen solid until you dig down into that ocean. So you may see some things that look similar to Earth, but you may see some things that are very different.
That voice you just heard?
I am Morgan Cable, NASA scientist.
I love it.
That's Morgan. She's probably one of NASA's best spokespeople for exploring our solar system's icy moons.
Europa is a fascinating place. It has this liquid water ocean that's about 3 times the volume of all of Earth's oceans combined. That's a lot of water.
To understand what makes Earth so special, sometimes you need to back up and take in the big picture. Remember, the cryosphere is every place on Earth with frozen water. And water is one of the biggest indicators for life.
Every place, at least so far, that we have found life, we found water along with it.
And so far, Earth is the only planet we know of with life. Although Europa isn't the only icy moon in our solar system, NASA has identified it as one of those places with key astrobiological potential. Morgan is a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon Europa. But she's also more than just a scientist working in a laboratory. She's preparing future NASA missions for success on the surface of alien worlds. This year, Morgan and her colleagues were in the field studying how life colonizes in fresh lava.
Earth, it turns out, has a lot of excellent, what we call analog environments, places that are similar enough to some of these other worlds that we can conduct some tests and we can do some analyses here. Now, they're not perfect, of course. They're not going to be exactly like Europa, but we can still learn a lot by testing in these environments. Some of these places include Antarctica and the Arctic Circle, but there are other places too, Alaska, Greenland, even Iceland. Any place where you have a lot of ice, because guess what the surface of Europa is made of? A lot of ice.
Studying the cryosphere doesn't just have big implications for Earth. It also matters for the frozen worlds in our own cosmic backyard.
If we're able to find life or evidence of past life on a place like Europa, that tells us that not only can life happen in other places, but it's common enough that it happened at least twice in the same tiny solar system. That means that the universe is wide open in terms of how much life we might find, the types of life we might find. It would revolutionize how we see ourselves and the possibilities for contact in the universe. It would be amazing. Oh, it's so exciting.
My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's an absolutely fascinating thing to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out and down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them, and you don't want to either.
But Chris doesn't spend weeks away from home and family for the views. Chris and his colleagues at NASA want to answer some pretty big questions by learning more about Alaskan glaciers and how they tick.
You know, why does NASA care about these? Well, they actually disproportionately contribute a large amount to sea level rise.
In the long run, as the Earth warms due to climate change, the big ice sheets and mighty outlet glaciers of Greenland and Antarctica stand to contribute the most to sea level rise, simply because the vast majority of the planet's ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places like Alaska and Patagonia that are contributing about 1/3 of all inputs to sea level rise, even though they account for only 1% of the world's ice.
Mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, these are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICESat-2 satellite and detailed airborne measurements to monitor changing ice.
What we're looking at is a legacy of the Ice Age. Permafrost and methane is a time machine. So what we're going to do is walk back in time. We're going to see old carbon, old bones, old environments, and none of those are in equilibrium with today's climate, so that's the problem. That world doesn't exist anymore, and it hasn't for 10,000 years. It was nicely and very delicately separated from this modern warmer climate by about this much moss. And when that moss goes away, whether for fire or for human disturbance or for warming, then all hell breaks loose.
Permafrost. It's maybe the part of the cryosphere that's most out of sight and mind. It's fascinating how it formed in the first place and how it got loaded with so much carbon. In a minute, we'll go back underground with Matthew Sturm from the University of Alaska Fairbanks. But first, let's meet Peter Griffith, NASA's project manager for the Above campaign, which supports more than 70 science projects studying forest and tundra vegetation, wildfires, animals like birds, caribou, and Dall sheep, methane emissions from expanding northern lakes, and the impacts of climate change on people in Alaska, Canada, and around the world. Many of those projects have some direct connection to permafrost.
Permafrost is the hidden cryosphere. It's the permanently frozen soil that surrounds the Arctic, all across Alaska, northern Canada, and then across Eurasia. The ground has been frozen during the ice ages.
During the ice ages, there was not enough snowfall in the drier regions of Alaska and Canada to form glaciers there, so the land was suitable for vegetation.
What happened is that over thousands and thousands of years, all of that plant material got compacted and frozen every winter and buried and pushed down, so that today there's 300 feet deep of frozen water and dead plants and some pieces of dead animals too. Sometimes you find woolly mammoths in the permafrost. But most of it, of the organic matter as we call it in the permafrost, is frozen plant material.
Some of that plant material is now thawing and decaying, releasing its ancient carbon into the atmosphere, sometimes in the form of methane gas bubbling out of expanding northern lakes.
We started this field campaign because the Arctic is the part of the planet that is warming first and fastest. And there are consequences to this for permafrost. So during the Arctic Boreal Vulnerability Experiment, we're studying permafrost with people on the ground, from aircraft flying over the region, and also from satellites in space.
Another way to understand the permafrost is to take a walk below ground with Matthew Sturm and into the U.S. Army Corps of Engineers permafrost tunnel.
And they've dug this tunnel back into the side of a hill about 200 feet, and it goes sort of sloping down so that by the end of the tunnel you're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and the mastodons that are frozen in it. There's sticks that are 40,000 years old, that you can touch with your hand. There's grass that's still green, that's tens of thousands of years old because it got frozen, right away, and it's never lost the green color.
But as fascinating as it is to see these relics of an ancient era, or to see a tree split in half by thawing soil, or even to light a ball of methane on fire from under winter ice, at the end of the day, Peter and his colleagues want to know just how much organic matter is frozen in that permafrost, and how fast it might be released.
Currently, we think that there is something on the order of 2 to 3 times as much carbon locked up as frozen organic matter in permafrost as there is carbon dioxide in the atmosphere. So releasing all of that organic carbon from permafrost into the atmosphere would be a real game changer. That would be a tremendous transformation of the planet's atmosphere. Now, the good news is that it would take a very, very long time for that to happen. However, we are warming the planet at a rate now that calls into question how quickly is that changing and what the consequences in the near future and in the far future are going to be.
We're at Vandenberg Air Force Base. We're about 20 minutes before the launch of ICESat-2. You might see the white light off in the distance. That's the Delta II rocket.
It kind of feels like an idea that was always going to just stay an idea. But no, it's real. It's sitting on top of the rocket.
And for me, it's kind of surreal. Like you say, it's been 10 years and it's hard to believe. It's like, we're really here? This is really about to happen? It's totally cool.
This is Dr. Tom Newman. Over the years, his work has taken him to some pretty remote areas to study changes in the ice regions of our planet. And his research, among many others, has defined the goals of the new NASA satellite, the Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2.
And we have ignition and...
The story of ICESat-2 really begins with ICESat-1. ICESat told us all kinds of cool things about the ice sheet and about sea ice that we didn't really know to ask. That data allowed us to measure elevation change of ice sheets, in a way that we hadn't been able to before, and showed that all the action on the ice sheets, the places that were really changing quickly, were around the edges. So when we were thinking about what could we do better next time, we knew that was one key component.
In addition to the edges of the ice sheets, ICESat-2 needed to measure a dimension of sea ice that remained elusive: its thickness. To figure out how thick sea ice is, you can measure the height of ice sticking out of the ocean, or freeboard, and compare it to the height of water between the sea ice flows, called leads.
The problem is, sea ice is really dynamic, and those cracks open and close various places in the ice pack throughout the day, throughout the year, and what we need to do is have measurements of the ocean whenever it's available, wherever it occurs in the sea ice pack.
To solve that problem, ICESat-2 was designed with a fast pulsing laser instrument to take precise, near-continuous measurements across its 3 pairs of beams. For 10 years, everything about the mission was designed to measure rapid changes in the most rapidly changing part of the cryosphere. But it has to get into space first.
But it's a huge transition going from the ground to in space. We've spent the better part of 10 years, thousands of people have been involved, and actually seeing the rocket there on the pad with all of that work kind of all put together in one place, it's pretty amazing. And then getting up in the middle of the night to go watch the actual launch, it's sort of surreal in a way, because you've put so much time into it for so long, and actually seeing it over there is like, whoa, you know, it's a big deal.
3, 2, 1, 0. Lift off. Push 1.
Thanks, sweetie. That was awesome. Totally cool. There it went. That was Atlas. The last Delta II, heading on up. So Atlas has been turned on over the course of the first few weeks of the mission, really culminating for us with the laser. So this is our first look at sea ice data from ICESat-2, and it looks fantastic. The signal levels look great. We've got plenty of photons there. We're capturing ridges. We can clearly see the ocean. All sorts of cool stuff in there. And this is just our first data. It's only going to get better from here on out.
The data from ICESat-2 is well on its way into digging deeper into the unknown dimensions of sea ice sheets, and glaciers. It will shed light on changes in sea level and global weather patterns, and once again find new things about ice we didn't know to ask.
So my heart is definitely racing. I don't know about anyone else's. This is the stuff nerds dream of.
10 seconds. 9, 8, 7, 6, it's gonna 5, 4, 3, 2.
That countdown you just heard? We'll get back to that in a minute. Last episode, we saw the epic launch of ICESat-2, NASA's newest state-of-the-art ice-observing satellite. But now that that's in orbit, the pressure to deliver results is on.
Between launch and, the first ground returns, it took 17, 18 days or something like this. It's a time when you're quite nervous.
9 years ago, Dr. Torsten Marcus took over as the lead project scientist for ICESat-2 during a time when the mission needed a champion.
We start fighting for a mission over, for 9 years now.
So when ICESat-2 was turned on for the first time 18 days after it was launched, only then would the science team know if the whole thing had worked. And it did.
First of all, it's kind of emotional, right? Being here, ICESat-2 was developing for 9-10 years. Project scientist, you live the mission, right?
If it sounds like there's a lot of noise in the background, that's because Torsten is being interviewed from a plane 1,500 feet in the air. IceBridge was tasked with the job of bridging the data between the end of ICESat's mission and the beginning of ISAT-2, about a 9-year difference.
The goal is that it would run until ISAT-2 launched and then would have overlap with ISAT-2 as well. So we can get a really long, well-calibrated time series from IceBridge.
As the deputy project scientist for Operation IceBridge, Brooke works closely with Torsten to make sure the two missions are syncing up.
The timing was everything during that mission, which was a real challenge because not only do we need to...
Basically what you need to take away is getting an airplane and a satellite in space to fly over the same flight path at the same time and collect matching data is really, really hard. IceBridge was tasked with two objectives. Check the accuracy of ISAT-2's data over land ice and over sea ice. They were able to lock in the land ice data fairly quickly in the mission, but the sea ice data...
It was really tricky. We waited day after day. Do we fly the sea ice? It's still on our list.
7, 6, it's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435 350.
Here's what just happened. A plane 1,500 feet up and a satellite 308 miles up measured the same sea ice at the same time. This moment finally linked veteran mission Operation IceBridge's data to that of its new sister mission, ISAT-2, two projects that, until now, were separate for nearly 10 years.
It's a very satisfying feeling because you do something that is meaningful and in the bigger picture, and yeah, it's very satisfying.
Our search for knowledge doesn't end here. Grace Follow-On and ISAT-2, the two satellite missions that launched this year, will continue to bring in incredible data for the foreseeable future. The steady drumbeat of campaigns in the field goes on, but most of all, the people who look for answers will never stop searching. And from our perspective, it's pretty clear why.
What is your favorite planet in the solar system?
My favorite planet is the planet Earth.
What? Earth? Really?
The Earth, obviously.
Favorite planet in the solar system? Earth, right? We live on it. It's a really important one.
Favorite planet is Earth.
Right.
Yeah. Yeah, so when you look out at the other planets, they're absolutely fascinating. They've got all sorts of interesting systems going on. They've got dust storms. But then when you're on another planet, looking back at Earth, I mean, it's just incredible.
Whenever you go in different places, it looks so different, so amazing. It's just, I love the planet Earth. It's just a very special planet. This is our home.
We've seen things far beyond the solar system. But even with all that, even the amazing things we've seen, one of the most amazing is the Earth itself.
It's got to be Earth. It's got to be Earth.
It's got to be here. I like the polar regions of here, of Earth. Yeah, sorry. It's very boring.
Earth is good.
Earth is good.
We live here, it sustains our life.
I'm not going to turn my back on it.
It's got water, it's got ice, it's got vegetation. I mean, it's rich with life. And so studying Earth is a very, very rewarding career. And I think if we were on any other planet, we would be trying to get to Earth as quickly as we could.
"14 days, 2 piston bullies, 4 people." So yeah, 750 kilometers, door to door. Recently, we just got back from Antarctica, where we completed about a 2-week ground traverse near the South Pole. We're basically driving piston bullies, tracked vehicles similar to the ones that groom your ski areas. Behind those piston bullies were 60-foot long plastic sled trains, and ultimately those trains carried things like our sleeping tents, fully erected and left standing during the day while we were driving, kitchen tent, fuel, generators, all sorts of cargo.
But everything we needed for the trip.
And from a both science and survival standpoint. So this entire traverse was in support of ICESat-2, which will launch later in the year.
ICESat-2 is all about measuring elevation, and a natural question is, how do you know you're getting the right answer? This is how we will know. We'll go out and collect a reference data set. We'll be ready to compare and evaluate, see how we're doing.
319 is feeling kind of ready. How you guys doing over there?
So the big measurement we were making was to measure the elevation of the ice sheet surface around our traverse, and we had the 2 GPS running, one on each vehicle, measuring that elevation. One of the other experiments we were doing is leaving out what we call corner cube reflectors to get an assessment of the pointing of ICESat-2. When we make an elevation measurement, how are we sure it's in the right place? So in this picture, you can see a bamboo pole with a little white cap on the end of it, and embedded in that cap, a little piece of glass about as big as your pinky nail, and calibrated to return green laser light from the satellite. Bounces off of this thing and goes right back up to the satellite again, super reflective. So these things, as Kelly has demonstrated, show up in data with altimeters like ICESat-2. When you first get to South Pole, and you're coming from McMurdo, which is a nice seaside town right at sea level, and South Pole is what, about 10,000 feet. And yeah, you notice it pretty quickly. The temperature is a lot colder than in McMurdo. It's probably 30 degrees, 40 degrees colder, and 10,000 feet higher. Walking from the camp to where we're putting in an array, for example, would be a 10-minute walk, maybe 5 minutes. A couple breaks on the way. You know, it's still pretty high.
The plan is to repeat this traverse for the next 3 years, so 4 years of data total, and that would last the mission lifetime, the mission requirement lifetime for ICESat-2.
ICESat-2 has 1,387 orbits, and so it's cruising around the world, and it's got these unique tracks that repeat every 91 days, and all of those tracks converge right here at 88 South. And so our route crossed, what, 20% of them? So we can calibrate data from 20% of our tracks with this stretch that we drove, and by repeating it every year about the same time of year, we'll have overlap at exactly the same time, but we'll also be able to figure out what's been going on in between, because we'll measure it in 2017 and then again in 2018, and you can see how it changes from year to year. So that'll be pretty cool too. It'll quickly become the best surveyed piece of either of the ice sheets.
This video is from the 16 October 2018 Northern Peninsula Ice Bridge mission. We're about 1/3 of the way into the flight right now in this video, and we have just finished our first transect across the Larsen C ice shelf from west to east. And we are making a right turn to get lined up for our second transect across the ice shelf. You can see here we're crossing some fairly large tabular icebergs. These are remnants of the breakup of the A68 iceberg off of the shelf last year. The big square-looking iceberg at left is the one that became somewhat famous in the media over the last few days. Now we're crossing some combination of open water and sea ice. This big, huge tabular berg ahead of us is the A68 iceberg. It's about 100 miles long, about 30 miles wide. And you can see the video here has been sped up by a factor of 20, and even at that, it still takes us quite a while to get across this thing. And you have to remember there as well that we were only crossing the northern corner of it, and even so, it took us a while. So now we're back off A68 iceberg, heading westbound. You can see the sun there. It's the afternoon, crossing a mixture of sea ice and icebergs, and this big white mass ahead of us is the Larsen C ice shelf, which we're just about to head back on.
There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For oceans melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean and it gets all broken and craggy and big chunks fall off. It's incredibly dramatic. Kulisuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. We slow down a little bit and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. We're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean ice interactions in Greenland as best we can with one mission. What we care about with OMG really is the breaking off at the edges. As the water eats away at the ice, then it can actually speed up that breaking off part. And when you dump more ice in the oceans, then it causes sea level rise. So OMG is really here to try and figure out how much are the oceans doing, how much is this kind of breaking off of the ice, it's called calving. How important is that relative to the melting at the surface? And more importantly, is the ocean causing some of this speed up of the calving? We think it is, but how widespread is it and how big an impact? Even the smallest iceberg looks gigantic when you're right next to it. We saw an iceberg that was grounded in the bay. Remember, 90% of the iceberg is below sea level. So if there's about 10 meters or about 30 feet of ice above sea level, then 300 feet are below. It's a reminder that a lot of the stuff we're trying to measure is hidden below the surface of the ocean, hidden below the surface of the ice, and peering down into both of those is really at the core of what OMG is trying to do. Every time a ton of ice comes off of Greenland, sea level goes up a tiny little bit, and it's coming off Greenland at billions of tons per year. It's interesting to meet some of the Greenlandic folks who have been here their whole lives. They've all watched the glaciers literally vanish before their eyes. They didn't need satellites and airplanes and scientists to tell them that Greenland was melting. They look out and see the glacier used to be here and now it's way up there. Sea level rise is really a global problem. It's something we can't just ignore. 2/3 of the planet are covered by the oceans, and it's really the same ocean. I mean, if ice is lost here, sea level rises back home in Los Angeles, rises in Southeast Asia, in Australia, all across the planet. Being here and seeing the ice disappearing and literally watching it fall into the ocean is really profound, and I think it's something that I hope that we help people understand with OMG, that we all live on the same planet and it's changing and we need to know how.
From space, we see deep into the heart and veins of our ever-changing planet. Pictures of Earth are worth more than 1,000 words. They are the blueprint for our future. To unlock the full potential of space's unique vantage point, we've created powerful tools. Tools that gather valuable data. Data that enables farmers to efficiently manage water and fertilizer for stronger food yields. Data that scientists use to monitor ticks and mosquitoes that carry harmful diseases. Data that first responders use to find the fastest routes to save lives. That's only a glimpse of what we can do today. In the future, when combined with AI and powerful computing, a broader range of space data would generate infinite solutions for Canadians. Imagine a future where we can use space data to better understand and predict the impacts of climate change, like rising sea levels, extreme weather, wildfire risk, and flooding. Measure the health of our forests and create predictive maps of pest damage and burn extent. Produce real-time dynamic navigation routes to protect whales and other endangered species. Ensure security and sovereignty in Canada's vast Arctic. Tomorrow's challenges require investing in innovative solutions today. Earth observation is key to securing economic opportunities and improving the lives of Canadians. Together, we can define Canada's future.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. Thank you for joining us tonight. My name is Mark Razzie from the Public Services Office at JPL, and again, want to thank you so much for joining us for this edition of the Von Karman series. Tonight, we're going to explore the infrared spectrum, or at least some of it. Now, William Herschel first discovered the infrared in 1800, but it wasn't until the mid-20th century that real research into that part of the spectrum began. But when it did, it began in earnest. There have been many instruments, telescopes, and spacecraft that have all worked to reveal mysteries hidden in the infrared, but there are still plenty of unanswered questions. Tonight, our guests, who are but two of very many people working on these projects, by the way, are going to talk about two upcoming missions that hope to deepen our understanding of our universe by continuing to delve into the infrared. Helping me out tonight with the Q&A is our co-host, JPL Public Outreach Specialist, Caitlin Soares. Hi, Caitlin.
Hello and welcome, everyone. As Mark mentioned, my name is Caitlin and I work in public outreach at JPL. We have a fascinating program for you tonight and we want you to be involved in the conversation. So please ask questions in the chat and we'll try to address as many of them as possible tonight throughout our discussion. If you don't see the chat for some reason, please refresh your browser and it should appear. And I'll turn it back over to Mark now so he can introduce our brilliant speakers for tonight's program.
Thank you very much, Caitlin. So our guests tonight are Dr. Dita Markovich, who is a research scientist at JPL working on the Euclid mission, and Dr. Phil Korngut, who is a research scientist at Caltech and the instrument scientist on the SphereX mission. Good evening, my friends. How are you guys?
All right.
Good. Super happy to be
thrilled
here.
to be here.
Thanks. Our pleasure. So Phil, to set the stage, would you be so kind to give us a little bit of a primer on the electromagnetic spectrum?
Sure, be happy to. All right. Well, when you think about fundamental measurements in astronomy, there's really one observable we're talking about, and that's electromagnetic radiation. Now, you're more familiar with that term by its colloquial term, light. And all the signals that we're measuring, from the gamma ray through X-ray and all the way to the radio, those are all just different flavors of light. And the parameter which governs that flavor is what we call wavelength. So what you're looking at here in this plot is the electromagnetic spectrum that is accessible to astronomers. That x-axis there in wavelength is a logarithmic scale, and it spans 15 orders of magnitude. So that's literally a factor of 1,000,000 times 1,000,000,000 in the available light that's out there. The way you think about those different flavors in terms of your real world is in color, except it's far outreaching from what your eyeballs are used to. If we go to the next slide, you can see in context the optical, which is every piece of light that you've ever seen in your life from blue to red, which spans only about less than a factor of 2 in wavelength. So that's a pretty wild concept to think about. There's 1,000,000,000 billion colors out there. You could see just over a factor of 2 of them. So there's all sorts of observables which can trace all sorts of stuff from astronomical objects. It's not a surprise why your eyeballs work in that wavelength range called the optical. If you click on the next slide, we'll show the spectrum, the emission spectrum of your very favorite source, or at least the one that is most common here on Earth, which is the star that is our hometown, or the sun, which is about on the order of 5,700 degrees Kelvin. And its spectrum looks like that, which peaks in the optical. On the next slide, we'll kind of zoom in on that neighborhood. And, the peak of the sun, which is right there around green at a few hundred nanometers wavelength, just redder than red, so at longer wavelengths than your eyeballs work at, is the near infrared. And that's the region that we're interested in discussing today. And there's all sorts of interesting sources out there. Nominally, things which are emitting thermally in the infrared, so things that are not quite as hot as the sun, that go down to thousands to even hundreds of degrees Kelvin. Now, there's a problem with doing that kind of observation here on our hometown of the Earth. If you click to the next slide, you can see what our atmosphere does. So while Earth's atmosphere is great for things like breathing and living on, it's not so great for looking through. So all of those magenta lines that you're seeing there, that's absorption features in our Earth's atmosphere. So, while air looks clear to you in the optical, if you look in the near infrared, it's not really clear at all. There's all sorts of stuff absorbing. Not to mention that everything, that's here on Earth that's, kind of room temperature is actually glowing in light and emitting. So it really makes sense when you're doing astronomy in the near infrared to get off of this planet and go up into space.
So, Dita, then, if you would be so kind, tell us why the spectra are so important in astronomy.
Yeah, I'm happy to do that. So I guess what I should say first is that astronomy is kind of like detective work. It's not quite like other science where you can, put something in a lab and poke it and see what happens and then, figure out the laws of nature that way. In astronomy, the things that we're interested in are really, really far away. So all we can do is kind of sit here and hope that information will, on its own come to reach us. And so things that we observe, we look at stars. And if you're a cosmologist like Phil and I, you look at things that are much, much further away than stars, like galaxies. And so what we do is we sit here and we collect the information that's coming to us from those galaxies. And the most common way this information reaches us is through light. We're talking about the electromagnetic spectrum today, so that's of course what I'm talking about here. And so this light comes from these really distant galaxies to us, and we build huge collectors of light or telescopes to capture it. And then of course we examine all the information. We try to get all the information that's in this light. And one of the things that we do is we break it up into its component wavelengths or frequencies or energies, which is basically the spectrum that Phil has been telling you about. And these spectra, they contain basically a fingerprint, a really specific pattern that tells us a lot about the chemical properties, the thermal properties, and the kinematic properties of the thing that's emitting that light. So the light source, so the properties of the stars and of the galaxies. And so we can have, like very small ranges in wavelength or frequency where there's a bit of extra light in there, and those are called emission lines. Or we can have part of the spectrum where there's a little bit less light. So if you show the next picture, you can see I've sort of made a picture that shows a kind of a pattern of these absorption lines where there's a little bit less light, and there's an emission light where there's a little bit more light, and this is a specific pattern that we can understand really well, because the exact pattern of the emission absorption lines comes out of quantum physics, and we can play around with this in the lab and actually calculate exactly what these lights might appear for, in different, if you have different types of stuff that's emitting the light, different gases at different temperatures. And what's also really cool is that something really interesting happens to this pattern, and if there's some kind of motion of the emitter of this light. So let me first tell you about the Doppler effect. So you might have heard of it before, and it's an effect that happens in sound, and it's I'm sure you've all, even if you don't know the expression Doppler effect, you would have experienced it, because an example of it is if you have an emergency vehicle that has a siren that's moving towards you, and if the emergency vehicle is moving towards you, it's as if the sound waves are getting squished together, and so the pitch of the siren, is higher than usual. And if the emergency vehicle is hopefully moving away from you, then it's as if the sound waves get stretched out and the pitch falls. So the siren, as it approaches you, it's high pitched, and then as it moves past you and goes away from you, the pitch falls. And something kind of similar happens in light, and it's really interesting. But the big difference is, one of the big differences is that the thing that is emitting this light needs to be moving with respect to the observer. So its speed with respect to you has to be a lot higher than of that emergency vehicle. In fact, this light emitter needs to be traveling at a significant fraction of the speed of light. So you might say close to the speed of light for this kind of shifting effect to be observable. So what happens is if you have a distant galaxy that is for some mysterious reason moving away from you, the wavelength, it's as if the wavelength of light gets stretched out. It gets redshifted, and so the pattern moves towards the red part of the spectrum. And if the galaxy was moving towards you, the light would get blue shifted. So this specific pattern, this fingerprint that we can understand, moves towards the blue. And so you can measure this red shift or blue shift. And about 100 years ago, there was somebody called Vesto Slipher who tried to measure, he looked at a bunch of things that he called nebulae, but we now call galaxies because we know that they're outside of our own Milky Way. So he measured a bunch of red shifts, and he noticed that in fact, there were mostly red shifts, and there was already a handful of galaxies where he actually found blue shifts. And then sometime later, somebody called Hubble came along, and he looked at this data and he supplemented it with other data. And he looked at it and he said, okay, let's measure the distances to these galaxies and see if there's a relationship between redshift and distance. And so if we look at the sky and we look at all of these galaxies and we measure redshifts, we might get a picture like the next picture that I have here. Like a lot after Slipher and Hubble. This was from an experiment called 2MASS. So here you have lots of little dots, and they have different colors, and the different colors correspond to different measurements of redshift. So this is what this would look like on the sky. But what if, so as I said before, what if Hubble said, what if we can measure distances to all of these galaxies and see if there's a relationship? In fact, there is a relationship, and I have an equation for you now, so brace yourselves. So if you show the next picture, it's the only equation, I promise, and it's just to illustrate the importance of the redshift distance relation. So what you're seeing here, on the left-hand side, there's a D with a subscript A, and that's the angular diameter distance, as we call it. And on the right-hand side, there's the letter C, which is the speed of light. We have the letter Z, which is the redshift, and then an integral of 1 over a function called h. That's called the Hubble function. And that function contains all the information, well, a lot of the information about what the universe is made of. And it tells you a lot about the history of our cosmos. So if you can measure the D, the distance, and if you can measure the Z, the redshift, so this is the distance redshift relation, then you can infer so much about our cosmology, about this H function, about what the universe is made of and its cosmic history. And so now, if I can show you a picture of what happens if you connect distances and redshifts together. So these dots on this picture, this is again from 2MASS, they're all different galaxies, and the colors denote the redshifts. And of course, distance is distance. And we sit in the center, we're the observer. And you can see that redshift increases with distance. And so when Hubble realized this, of course, he didn't have a picture as nice as this, but he had something like that. When he realized, when he saw this relationship, he said, oh, wait a minute, that must mean that the universe itself is expanding. Space itself is pulling these galaxies apart. So that those that are the furthest away from us seem to be moving away from us at the highest speed. And so this way, if we can make these kinds of three-dimensional maps of the universe, of the distribution of galaxies in the universe, we can look both far away into space, but we can also look far away into the past. And that's because light has a finite speed. So that if I'm looking at a galaxy with, of course, a big telescope, it's very, very far away. What I'm seeing is not the galaxy as it is today, but the galaxy as it was when light left this galaxy, which may well have been billions and billions of years ago. And so this way, as we look into the distance, we look into the cosmic past. And Phil, I think, has a nice picture to show you what happens if you look through, what you might see if you look through the cosmic past.
Right. Yeah. So if we bring up the next slide, let's look at some of the implications of those concepts that Dita just introduced. Right. So this figure is a cartoon of the history and the evolution of the universe. That arrow that goes from left to right represents time from the very beginning until today, which is all the way on the right side, where you see today the structure of the universe as we know it, that has all sorts of galaxies populating this cosmic web of structure. And this diffuse light that's out there today that came from all sorts of tidal interactions in the history of the evolution of galaxies, where stars get flung out way into their exerts. So if we think about observing today in the near infrared, all of those galaxies in their what's called a rest frame, so in today's unredshifted wavelengths, they're emitting in the near infrared, and they peak there because they have a bunch of stars which are cooler than our sun. But if we think about now looking further away, hence further back in time, also, since the universe is expanding, we're looking at sources that are redshifted far away. So if you go all the way back to about, only, 10 to tens of billions of years ago, the first stars and galaxies, which were forming out of the neutral hydrogen, which cooled and condensed, and those first stars turned on, emitting in their rest frame ultraviolet, so really blue and really hot, that's now redshifted into our observation. So when we talk about the infrared background, another term that we use is the extragalactic background light, we're thinking about the integral. We're measuring the integrated light production in all of cosmic history. And it turns out that when we look at the structure today in galaxies, the way they're populating in this web, all of that structure was seeded at the very earliest epochs, right after the Big Bang, in an epoch called inflation. So there are these two epochs of rapid expansion in cosmic history, that early epoch of inflation, and then today, where dark energy is taking over and is expanding our universe rapidly. So the large-scale structure today is tied to those earliest epochs through what was seeded as quantum fluctuations, which I'm going to pass it back to Dita to tell you a bit about.
Yeah, Dita, if you would be so kind, can you elaborate on those a bit?
Yes, I'm happy to. In fact, I can even show you an animation. So if you show the next thing that we have to show. Thank you. So there's something really strange happening if you look at empty vacuum of space. So if you were able to go into the vacuum and see what it looks like, it might look pretty boring to you. But if you could zoom in and look on the tiniest microscopic quantum scales, you would see that it's anything but boring. Now, of course, we can't do that. We can't see these scales. Even with the best microscopes, we can only see hints of it. And we certainly can't observe what we, this kind of thing that I'm showing you here. And what I'm showing you here is called quantum fluctuation. It's kind of like this bubbling on quantum scales. And what's happening is that basically out of nowhere, pairs of particles and antiparticles are as if they're borrowing energy from empty space and coming into existence, and then a small fraction of a second later, they're annihilating each other and returning this energy back into space. And this was actually also happening at the very, very beginning of the universe, except that back then things were even stranger. At the very, very first moments of our universe, the universe was really dense and really hot, and then these things were bubbling, the quantum fluctuations were happening. And suddenly, space itself started to expand in a really, really dramatic way, not just expand, but accelerate. So it was speeding up, the expansion was speeding up, as Phil mentioned. And we call this process in the early universe, we call it inflation. And we don't really understand what drove it and why it happened. And we don't understand the thing that's powering it. But as the universe expanded, the density dropped and it cooled. And this thing that was powering this inflation, it underwent something that you could call a phase transition. So what happened was that the cooling pushed this strange stuff to decay into more familiar particles that make us up and that we can interact with. Also a bunch of other weird stuff on the side, but that's too. And so the universe was expanding, and as inflation was over very quickly, a very small fraction of a second, what it had done is it pulled these quantum fluctuations from these tiny microscopic scales to macroscopic observable scales. And so these little bumps, they were kind of small and big bumps on all scales, were frozen in, so they didn't bubble anymore, but they were there also on observable macroscopic scales. And so what we had now, after a very small amount of time at the beginning of the universe, we had this lumpy soup that was made up of particles of normal matter, but also of dark matter. And so this lumpy soup, of course, was being governed by the laws of physics. So it felt gravity and it felt pressure. So these little lumps in the soup felt pressure, and they suddenly started inflating into these bubbles of sound. So sound was propagating through this early universe. And now, this situation kind of lasted for hundreds of thousands of years. So we've gone from a fraction of a second to hundreds of thousands of years. And after some hundreds of thousands of years, this sound stopped propagating because the density dropped so much. And these bubbles of sound that were propagating through, they got frozen in. So I'm going to have an animation for you to show you these bubbles of sound and what happened afterwards. So the bubbles of sound, so if you go to the next animation, please, the bubbles of sound were also, influenced by gravity. So the shells of these bubbles fragmented under gravity and collapsed into galaxies. But galaxies also formed at the centers of the bubbles, and that was because of dark matter. So dark matter didn't feel this pressure at the beginning of the universe. It didn't, sound wasn't propagating through it. So it kind of remained in the locations of those original lumps. And then it also attracted lots of normal matter towards them. And that's what that normal matter then fragmented under gravity into galaxies and collapsed. And the really cool thing about these bubbles is that the physics to calculate their size is pretty straightforward. So we can actually calculate how big we expect them to be today. So this is 150 megaparsecs. And so if we look at the sky and we know how big these bubbles are supposed to be, if we can see them and measure how big they appear, then we can measure distances. So it turns out that these bubbles were discovered in astronomy about 15 years ago. They're called baryonic acoustic oscillations, formally. And they are an amazing measure of distance throughout a huge amount of the universe. So looking back into the past, you can measure distances to really distant galaxies, but you can only do it statistically. So using this measurement of distance that works so well, and then measuring the redshifts of the galaxies that make up these bubbles, then you can calculate this distance redshift relation, and you can see this effect. You can see the effect that as Phil mentioned, that the universe started accelerating. So the expansion of the universe started accelerating again billions of years after inflation, and this accelerated expansion we say that it's fueled by dark energy, as Phil mentioned, and we don't really know what dark energy is. And so, in fact, dark energy and inflation are two of the biggest mysteries of modern physics. And that's really exciting to work on.
That's really, really cool. So let me call for the next slide and kind of summarize what you two have talked about so far. So there have been two epochs where the expansion of the universe was speeding up. The first epoch was called inflation. and then the current expansion, which is due to dark energy. There's a wealth of information related to both of these phenomena buried in the large-scale structure of the universe, and these two missions are going to help us, pull some of that out. So the Euclid mission will probe the structure at about half the age of the universe, if I got that right, and from that we'll infer what dark energy is doing to the universe's expansion today. And then the SphereX mission will survey a huge volume of large-scale structure in the nearby universe, and from that will teach us about the energy field or fields that drove inflation in the first instance of cosmic history. So, Phil, let's bring you back. If you please, tell us about the SphereX mission that you're working on.
All right. Yeah. Well, I've got an overview on the next slide. And so SphereX is indeed another, it's a tortured acronym. It stands for the Spectrophotometer for the History of the Universe, Epoch of Reionization Explorer. And it's designed really as one of the first missions where not only are we going to make a map of the whole sky in imaging, but we're going to take a spectrum towards every single pointing at a resolution of 6 arc seconds in the entire universe. And from that huge data set, we've optimized further to really get at these 3 main science themes. The first is, as we've been discussing, to measure the large-scale structure in today's universe, so tracing all the galaxies as they populate this cosmic web. And by doing statistics on the relations and how clumpy and clustered they are, to tie that back to those quantum fluctuations at the real dawn during inflation. But also, we're going to measure that integrated light field in the extragalactic background light. And from that, to disentangle the various components which came from that epoch of reionization, or the time when those first stars and galaxies were turning on and evolving through cosmic time till today, where there's all sorts of diffuse light that's gotten flung out to the far reaches of exurbs. But also at our more close to home, in our own neighborhood of the Milky Way, so our parent galaxy that we live in, we're going to use this very this significant feature of absorption that comes from ice, so just water ice. And we're going to survey our galactic plane in our neighborhood for water ice absorption. And as we know, at least on Earth, where we're looking for life, we're looking for water. And so most of the water in the universe is actually not liquid, it's in ice form. So SphereX is going to survey the galactic plane for water ice absorption. On the next slide, I'll show you a movie of how we implement this. So SphereX, it lives in what we call a sun-synchronous low Earth polar orbit. So at about 700 kilometers over the Earth, we're going around on this terminator line. So it's always sunrise or sunset for SphereX. And we keep our solar panels there to our back to the sun to keep us nice and charged up and powered. Now you can see as we pan up, SphereX has these set of 3 nestled shields. We call them photon shields. Their job is to block the radiation which is coming up off the Earth, the thermal radiation from the Earth, as well as the sunlight from getting to the core of SphereX, which is that telescope you can see there. This telescope, because we're working in the near infrared, has to be cooled to really low temperatures, and we do so passively using the actual cold of deep space. Doing that, we can cool this telescope down to 40 Kelvin. Most of us, at least in America, think in terms of Fahrenheit. That's the equivalent of minus 387 Fahrenheit. And we need to get down that low to control the emission, actually the light emitted from our telescope. At the core of SphereX is what we call a linear variable filter, an LVF, and I've got a picture of one on the next slide. And this is where we get all of our spectroscopic power. It's a really efficient way of doing this in space. It's a little piece of sapphire, which has a very special optical coating on it, which only transmits selected wavelengths depending on where you land on the filter. So in that picture you're looking at, you could think of on the left, it would only let through bluer light, and then towards the right, it would let through the redder light. So depending on where a source or a galaxy lands on our filter, we're measuring it at a different wavelength. Now we use these linear variable filters in concert with a wide field telescope, and if you go to the next slide, I'll show you how that looks. So the telescope is made entirely out of aluminum, and it's actually a pretty modest size. The aperture, or the primary mirror, is only about 20 centimeters, so kind of basketball sized. And if we cut it in half there, you can see we've got 3 mirrors. Now, a telescope's job is to take light from the other side of the universe, so collimated light that has parallel rays, and it brings it to a focus at what we call the focal plane. That's highlighted in that square there. At that focal plane, we place an assembly of 3 detectors, each of which has their own linear variable filter. So depending on where the light hits, we're measuring it at a certain wavelength. So you can see that light going through at a certain position. We'll make an image, and it might look something like what you see on the left there. We tally up all the light that got detected there, and from that, we've now made a single point on a spectrum. If we move our telescope so that that same source lands at a different position, so we dithered it, now we're measuring it at a different wavelength. We make another image, we add up all the photons that we detected, and then we've got another point on our spectrum. If you go ahead and repeat that about 50 times, we'll build up an entire near-infrared spectrum for that source. If you go to the next slide, so if we were to do this only for an individual source, that'd be really inefficient. But the beauty of SphereX is that we're multiplexing heavily. So in this animation, I've hid that center LVF, and instead we're placing a simulated image of what SphereX's sky looks like, put it to scale on that detector. And so now that we've flown in, you can see that we're measuring simultaneously a spectroscopic sample for hundreds of thousands of sources at every moment. So we measure hundreds of thousands of sources at each time. We take about 600 exposures per day, and then we do that relentlessly for 2 years, building up spectroscopic data set for billions of objects. On the next slide, we show you how we do that. So again, we're going around the Earth, around that day-night boundary, and we dither our linear variable filters around as we fill in those gaps. And so we put every single position on the celestial sphere to every position on our focal plane, and then we're measuring it at all the wavelengths. So as the SphereX goes around the Earth and the Earth goes around the Sun, it gets modulated and moves around, and in 6 months' time, we've built up a spectrum towards every point in the sky. We do this 4 times, and to build up a redundant spectroscopic sample to build up that robustness. So on the next slide, I'll show you a simulation of what we might expect from the SphereX dataset. And this is super exciting. We're flying through now. I think it's important to convey to you that this is actually, it's not an artist representation. This comes from an actual simulation that was done by our colleagues at Argonne National Labs, who, using what we know about the contents of the universe and the large-scale structure, simulate with 1 trillion particles in a computer that universe throughout cosmic time and populate the galaxies that live within this dark matter web. So that blue puffy stuff that you see as we're flying through, that's the dark matter lattice. And so this kind of gives you a scale of just the vastness of the data set. I should also mention that what we're flying through right now is about 1/200th of what the SphereX data set is going to look like. And once we have this 3-dimensional map that has all of these galaxies spread out in space, we'll do all our statistics on their clumpiness, how they're associated with their neighbors, on all sorts of scales, including the large scales. And from that, to learn to tie that all the way back to the quantum fluctuations which seeded that large-scale structure at the very earliest epochs of the universe. So as we're flying through, we're flying away from the observer, so we're looking back in time, earlier and earlier in the universe's history. And you can see as we start getting out here, the number of galaxies is going down. Now, that's not because the number of galaxies in the universe goes down there. It's because this is a simulation of the selection function of SphereX. So it's tuned to our sensitivity and our wavelengths and what we've optimized our survey for. So now, as it's getting sparser out here, is a good time for me to turn back over to Dita and Euclid, because that's where they start to shine and pick up where we left off.
Yeah, Dita, if you could hop back in here, and tell us about the Euclid mission that you're working on. This flyby is so cool.
Yeah, I'm really happy to. Yeah, so basically Euclid takes over just about now at a redshift 0.8, and it's aiming to find galaxies between redshift about 0.8 to 1.8, and that redshift range corresponds roughly to the time where dark energy was really just starting to become important, kicking in, and the universe was starting to reaccelerate its expansion. And so Euclid will be aiming at this range, and we will be looking at basically emission lines that correspond to a certain quantum transition in hydrogen, and that happens to fall in the lab. It falls into the visible part of the spectrum. But once you get redshift, once you get the universe expanding and looking at these galaxies, this feature, or this part of the fingerprint in the spectrum of galaxies, gets redshifted into the near infrared, and that's why Euclid has one of the two instruments is an infrared instrument. But generally, Euclid looks a little bit different to Spherex. The configuration is a little bit more familiar, and it will also be orbiting much further away from Earth. So if you show the next graphic that we have, you'll see that the Euclid spacecraft we will be sending it to something called the second Lagrangian point of the Sun-Earth system, which is about just under 1 million miles away from Earth, so far outside the Moon's orbit around the Earth, and it will be orbiting the Earth and the Sun simultaneously at that point. And the reason why we want to go to the second Lagrangian point is it's a particularly stable point in the Sun-Earth system, and the reason why that's important is because if you go there, you need less fuel to correct your orbit. Obviously, the amount of fuel is limited because this thing is very far away. It's not like there's a gas station there, a hydrazine gas station. So of course we want to conserve fuel, and that's why it's important to go to one of these stable points. And so the spacecraft itself will look. I have a little graphic that will show you what the spacecraft will look like. This is CGI, but it almost already looks like this. In fact, the payload module just arrived to Italy this week, where it's being assembled together into the full spacecraft that you see spinning on your screen. So this is what Euclid will look like. So you have this cylindrical part that's on top now. That's the telescope part. It's a reflector telescope. It has 3 mirrors, and the primary mirror is 1.2 meters in width, which I guess is about 4 foot. And so that's the telescope part. And then the middle part is the so-called focal plane, where the light from the telescope will focus, and it contains 2 instruments. One is a visible light instrument that I'm not talking about today, and it's just made up of similar chips to the detector chips that you might have in your camera phone. And then you have a near infrared detector. It's also just an array of 4x4 chips. And then at the very bottom, or at the very top right now, is the so-called service module, which contains a computer and the fuel tanks. And that computer basically controls where the telescope is pointing, and it's also talking to Earth. It's talking through 3 main really big antennas in Argentina, Australia, and Spain, so that, as the Earth spins, we can stay in contact if we need to. And then you have, of course, this flat bit on the side, I guess on that side for you, where that's the solar panels, basically, and it's also a shield that shields the telescope and the electronics from solar radiation, which might heat it up. But it also, of course, powers some of the electronics. So the 2 instruments in the focal plane will be taking images of the sky by collecting the light through the telescope. And let me show you what those images might look like. So if you show the next picture that I have for you, so in the near infrared instrument, we'll be taking images in the infrared with 3 different filters, which will just be fields of galaxies. But then there will also be a spectroscopic exposure. This is called slitless spectroscopy, where the light from all the sources in the field of view will be going through kind of a glorified prism. And these little lines that you see in this picture are basically the spectra of distant galaxies, which are the little ones, and then the very saturated spectra of the stars in our Milky Way galaxy, which we don't care about in this particular context. And so the really tricky thing here is that your field of view is going to be full of all these overlapping spectra. And that will create, a trick. It means that we need to use very sophisticated data analysis methods to extract those spectra, those emission lines, and those redshifts. And so one of the ways we're going to do that, which is basically the simplest way, is to have these prisms, these fancy prisms. We're going to mount them in the telescope, several different ones at different angles, so that this picture will be rotated and it will be easier to disentangle these different spectra. But also we've been building, for years, tens and hundreds of people have been building this sophisticated software pipeline to extract all of these really tricky things. And so we'll get spectra of tens of millions of galaxies all across the extragalactic sky. And we will also make three-dimensional maps using these spectra, and we will statistically extract those acoustic bubbles and connect redshift to distances that way. And so we will try to reproduce what Hubble did 100 years ago, hopefully do something a little bit better than that. And so let me show you what Hubble did 100 years ago. If you look at the next picture, that's actually Hubble's plot from his paper, where he plotted velocity against distance, and velocity corresponds to redshift. And you see this line of increasing velocity with distance. Of course, he got the numbers quite wrong, but the trend was still there. We know the universe is expanding. And so if you zoom out massively now, you get a plot like this, which is what we're doing nowadays in cosmology. And so it's not just Euclid. There's been several experiments that have been trying to make this connection. And so there's been several ground-based experiments, and their results, specifically to do with redshift distance relation, I've put on this plot with the colorful single dots. And then I've shown you what we think Euclid will do and how it will fill this gap in distance and redshift with very, very small error bars that you can't even see because they're hiding behind the points. And so this is what Euclid will do. And so I've put on here what experiments have done so far and what Euclid might do. But I've also put four lines on here. And these lines, they correspond to different universes, different types of universe that we might live in. And you can see that even already all the data that exists is lying very close to this solid line. And this solid line corresponds to a universe that is only 5% made of regular matter that we're made of, so-called baryonic matter. 25% of it is made of dark matter, and 70% of the universe is made of dark energy. And that's what all the data is pointing at. And that's what we're trying to do. We're trying to do with Euclid and with SpherX and with all these different experiments, is try to really get this data really, really precisely, make these lines really, really precisely, and try to understand all the properties of dark energy and how it impacts the accelerated expansion of the universe, and of course of inflation in the case of SpherX, and try to understand what that implies about fundamental physics. And I personally am really excited about that.
Thank you so much, Dita. That is just so cool. So let's bring Phil back, and then just let me mention, as of now, Euclid's scheduled to launch in a little over a year, and SpherX in just a few years. And I also wanted to note that, as many of you that are familiar with NASA may already know, all of this data will be publicly available.
Yeah. So, I think I hope we conveyed some of our excitement for this upcoming, missions. And, we've concentrated, Dita and I are cosmologists, and so that's kind of our area. But I think what's really going to be exciting is that we're shoveling all of this data just out into the community, the astronomical community, but also just the general public. And those data sets are going to have so much information. Just in the case of SpherX, there's going to be billions of galaxies with spectroscopic data, hundreds of millions of main sequence stars, hundreds of brown dwarfs, and all sorts of other stuff. Euclid is going to cover supernovae. They're going to do gravitational lensing. There's going to be, millions of galaxy mergers. And perhaps the most exciting stuff is just what we haven't even thought of yet. Right? The discovery space, when you do these kinds of huge surveys and just, deliver a really big data set out into the world of astronomers to mine and glean as much information as possible out of there. If I had to bet right now, I'd say the most exciting thing to come out of SpherX is really something that we haven't thought about right now. So I'm really excited, and I hope we conveyed some of that excitement to you today.
Oh, yeah. Very cool, you guys. Both of you. Thank you so much. It's going to be great to see just what becomes of all this great data. So I think this is a great time to see what kind of questions we have out there. So Caitlin, what are you seeing out there in the media world?
Sure. So this one is for Phil. Musical Wolves on YouTube asks, can Spheric see a galaxy behind a galaxy? Does anything block its view? Is it possible for it to see through?
Well, so it's an interesting question, and it depends on the contents of the two different galaxies and what the line of sight that goes through it. So that absorption features, those will imprint different features. So if you have like a background illuminating galaxy, and let's say really young and has lots of star formation, and lots of UV, so really blue, and then the galaxy that's in front of it, could have lots of molecular clouds and dust and stuff. What you would see from the background source would have an absorption fingerprint from the foreground source. So, it's hard to disentangle those. We always have to deal with the resolution of our, we can only measure so fine of a thing. We use the word confusion in astronomy, but mean it literally. But the beauty of spectroscopic is that, if you have two spectra that are on top of each other, and if you have a high redshift galaxy and a low redshift galaxies, you can see by separating out the colors the different stuff that's in both of them.
Great. Thank you. We have another one. This one's for Dita. This is a good question. How far away does something have to be for it to redshift?
It's not about distance, really. It's about this apparent motion of it with respect to the observer. But I guess you could be asking actually about how far does a galaxy have to be in order for the expansion of space to redshift it. And I mean, in principle, it's not a hard limit, it just becomes more and more redshifted. So it is really about the apparent velocity. But it's just that the further you look, the more it seems redshifted, which has to do with the expansion of the universe. But of course, there are also galaxies do actually move around because of gravity as well. So this is actually a really interesting topic that I work on, but I definitely don't have time to talk about it. But there's something called redshift space distortions, which means that the galaxies are moving around a little bit as they're kind of going with the expanding space. And those redshift space distortions actually can tell us a lot about our theories of gravity, and we can test Einstein's theory with that, and that's also really exciting.
Thank you, Dita. That is very exciting. I think we have time for one more question. This one I think would be for Phil. So Ray on LinkedIn asks, how fast is the universe expanding? Does it expand at the speed of light?
So, okay, when we talk about, that plot that Dita showed, we call that the Hubble flow. And if you look at what we call H naught, or how fast it's expanding today, it's around 67 to 70-ish kilometers per second per megaparsec. Okay, so let's think about that for a second. It's actually a very convenient unit because we think about, okay, a megaparsec, that's a huge distance. So let's just answer that question at a megaparsec, which is a distance that's pretty cosmologically far away from us. But that means that those galaxies are basically moving away from us at 70 kilometers per second at that distance. So that's how far away. Also interesting about that expansion rate, if we now think, okay, kilometers per second per megaparsec. Okay, kilometers is a unit of distance, megaparsec is a unit of distance. So you can convert things around and those distance cancel out, and then you're left with 1 over seconds. So it's an inverse time. If we invert that time, you'll get something around 14 billion or 13.8 billion, and that's the age of the universe.
Wow. Well, thank you very much, Phil. Thank you very much, Dita. So, folks, that's about all the time we have tonight. So I want to thank both of you, Dita, Phil, thank you so much. Caitlin, of course, all the folks behind the scenes, and of course, all of you out there for tuning in. As Caitlin said earlier, this is your space program, and this is one way for you to participate in it, and we appreciate that, so thank you. So please join us next month when we'll talk with JPL scientist Josh Willis about the Sentinel-6 Michael Freilich satellite's first year in space. That'll be a good one. Until then, be safe and stay well. Good night.
Get an inside look at NASA Glenn Research Center. From wind tunnels to drop towers and vacuum chambers, our virtual tours offer you a 360-degree view behind the scenes of our world-class facilities and labs. It's where we simulate aircraft flight conditions on Earth and the harshest conditions found in our solar system. Tap or click the arrows or use the menu on the left to navigate to each area within the facility. Tap or click the icons within the tour to view videos, images, and see testing in action. So go ahead, explore NASA Glenn, and learn how we develop and test innovative technology for aeronautics and spaceflight.
Today, we're going to talk about robotics on the International Space Station. Right now, there are several types of robots in orbit. There's a robotic arm that was used to construct the space station. There's a dexterous robotic space handyman. There's even robots that school children control by writing programs. We'll learn about those and some pretty special robots here on Earth. Join me as we go on board the ISS to learn more about robotics. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston on 2 for velocity confirmation. Assembly is 45 and 46. We're moving on to step 5.
You want to go right now for that activity?
Copy. Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
In this episode of Station Life, we're going to talk about robotics on the International Space Station. We'll hear from astronaut Mike Hopkins and what it takes to control the Canadarm2 robotic arm. We'll take a look at how robotic technologies from the International Space Station are helping lives right here on Earth. We'll have an interview with astronaut Karen Nyberg, one of our most experienced robotic arm operators, and the role robotics plays on the ISS, and hear stories of using Canadarm2 to catch dragons, among other things. So don't go anywhere. We've got a lot of robotic action coming right up.
One of the things that's really interesting with the Canadarm2 on the space station is that it has the ability to inchworm around the space station. It has 7 joints, and that makes it analogous to the human arm, but it also has a symmetric design, which means the base and the tip of the arm are symmetric, and there's an elbow joint in the middle. This means that what starts off as the base can be then maneuvered and released once the tip has grabbed onto another location, and then that base becomes the tip. So imagine my arm as I go from here, as I'm moving the arm here, I can grab on this end and release this end, and I can move around now. This allows me to inchworm around the space station and allow me to increase my range and in order to service things and also to do surveys and get the arm around this ISS. Like many people in the world that have a space passion, we all want to become astronauts and go into space. What I realized as I was growing up was that there are other areas that one can perform in the space program, and that was to become a flight controller. Once I became an active flight controller, I remember being in the Mission Control Center and sitting down and about to do an operation which I had written a procedure for. As the operation was beginning, I was looking at the numbers on my console, I was looking at the details of the operation, and I suddenly looked up at the monitor and I saw this beautiful view of the Earth going by. And I saw the Canadarm2 moving across this view, and it just sunk in that this is me. I'm in space. I didn't have to be an astronaut to get into space. I'm a flight controller and part of this beautiful program. And I could see my nation's arm moving, and it just gave me this wave of energy, and I just fell in love with my work. But of course, when that happened, I had to re-lock onto my numbers and focus on the job at hand, but it was a really fantastic moment, and I'll never forget that. My name is Cam Bahrami. I'm a robotics flight controller for the Canadian Space Agency. I'm stationed here at NASA's Johnson Space Center in the Robotics Flight Control Group. My responsibilities here are to support and execute the robotic operations on the space station using Canada's robotic system.
Did you know that we call operating the Canadarm flying the robotic arm? That's because it's a lot like flying an airplane. I mean, it's got hand controls, you can pitch, you can yaw, you can roll, and you have to be pretty precise. Watch astronaut Mike Hopkins describe how we use the Canadarm to catch cargo vehicles arriving at the space station.
Okay, hey everyone. Yesterday we had the opportunity to catch the Orbital 1 Cygnus vehicle, also known as C. Gordon Fullerton. And I'm going to take the opportunity today to talk about the controls that we use for the robotic arm. And so we're actually down in the cupola right now, and this is where we control the robotic arm when we go out and we grapple one of these vehicles like the Cygnus vehicle that we did yesterday. And so this is the control station, and what you see over here on my left, this controls the translation of the robotic arm. And then over here we have rotational control. And then this middle computer is where we actually take the robotic arm into the different modes that we do have. And then on our left over here we have a control panel for the various monitors. So what we're doing when we're grappling is I'm watching on this monitor basically a target on the vehicle, and I've got an overlay on it that allows me to line up the robotic arm with that vehicle, and I just drive right in. Now, I wanted to take advantage today though, because we have a pretty special opportunity here to show you a unique view of the robotic arm. And so if we look out one of the cupola windows here, you can actually see the end effector of the robotic arm. And we don't get a chance to look at this view very often. In fact, today we were doing an inspection on the end effector. And so if you look in the middle, you can see those cables. Those are what we call the snares. And when we go over the pin that's on the vehicle and I pull a trigger, it causes those cables, those snares, to close around that pin. And that's how we grapple onto a vehicle. And actually you can see up above as well, that's the camera that is giving us that view, and that's a pretty unique view for us, and so just wanted to share that with you.
Clearly, the Canadian Space Agency's robotic arms are technological marvels in space. You'll be happy to know that the same technologies are saving lives here on Earth.
1981 marked the debut in space of one of Canada's most iconic symbols, Canadarm. Developed for Canada by McDonald, Detweiler and Associates, formerly Spar Aerospace, the first Canadarm and its descendants, Canadarm2 and Dexter, are in great part responsible for the successful assembly and operating of the International Space Station. Now the technology behind these robots is finding its way back to Earth. By the end of 2014, an estimated 24,400 Canadian women will have been diagnosed with breast cancer. Early detection and treatment make a difference and help save lives. Researchers at the Centre for Surgical Invention and Innovation turned to Canadarm technology to develop IGAR. It is a promising platform offering one-stop diagnosis and treatment for patients with a high risk of breast cancer. Currently undergoing clinical trials, IGAR is one of the first robots of its kind designed to work inside an MRI scanner that can show the size and location of tumors more accurately than a mammogram or ultrasound scan. Thanks to its delicate and precise touch, the robot will be able to perform biopsies with pinpoint accuracy, analyze them, and treat early tumors without open surgeries. The platform will also help in detection and treatment of lung, liver, kidney, and prostate cancers, and might also be used for delicate spinal surgeries. Thanks to Canadian Space Robotics, this technology is a step towards a future where surgeons can rely on robots to perform intricate medical procedures that will be less invasive, less painful, and will allow patients to recover faster. Canadian Space Agency, thinking outside of the globe.
My name is Terry Fong. I run the Human Exploration Telerobotics project at NASA, and what we're doing is developing robots to improve the way that humans live and work in space. As humans go further and further into space, as they go to Mars, one of the big things that we're going to need are robots to help humans live and work when they're very, very far away from Earth. You know, if you think about being on Mars, one of the big challenges is how do you carry out work on a surface? How do you work outside of a habitat? And so one of the things we're trying to do is create robots that can work ahead of humans, robots that can work in support of humans, and robots to follow up, doing those things that humans need robots to do to finish up work. I'm just really excited about the idea of humans and robots working together. Well, frankly, that's the future.
Well, guess who we have with us today? We have with us none other than one of our most experienced robotic operators and leaders in the astronaut corps in that category, Dr. Astronaut Karen Nyberg. Welcome to Station Life.
Thank you very much.
I don't get enough of Karen. We actually sit right next to each other. Our office desks are right next to each other. But she is someone that I greatly admire for all of the experience that she brings to the International Space Station. She has been part of the construction work on STS-124.
That's correct.
She helped to bring a module, I'll let her talk about that in a second, and attached it to the space station. And then she lived on board the space station during Expedition 36 and 37 and did a number of tasks with the robotic arm at that point. And so there has been rarely anyone else that has touched that robotic arm control than Karen Nyberg. So please, Karen, tell us a little bit more about the experience that you've had operating robotic arms on board the space station.
I've been very lucky. I've gotten to do pretty much everything that it was designed to do with it. as you mentioned, STS-124, we brought up the Japanese laboratory in the payload bay of Space Shuttle Discovery, and we used the Canada arm to take it out of the payload bay, move it around, attach it to space station. So that is one of the big tasks that the arm was designed to do originally, is carry heavy or big masses. And
Kibo was one of the, or we call Kibo's the whole complex, but
right.
the pressurized module is the largest, is
right.
it not?
It is. It is.
And talk about, because didn't you also on your shuttle flight operate the PDRS, the shuttle arm?
I did.
Okay.
I did.
Talk a little bit about, because this is exciting, the difference between that arm and the station arm in terms of the joints.
Right. Well, the shuttle arm was pretty much fixed at the shoulder where you could have some pitch and yaw. The station arm also has roll at the shoulder, which adds another degree of freedom, so you have a lot more motion with the arm. And also you can move the location of the station arm.
Yes.
On station. So you could go along the truss and move it to different places and move it to the lab. And they do this little inchworm maneuver, they call it, where they attach one side, release the other, and inch it along the station to different spots.
That's creepy, but also kind of exciting at the same time. And so you did this motion, which, what do we call this one? The pitch plane?
Pitch plane, yeah.
We can only do that with the station arm.
Right.
And that's also what kind of makes it exciting, versatile, and dangerous at the same time, right? Because you can be moving, like this part of the arm can stay still, and this part can be moving around.
Right.
And there's just a ton of stuff you got to be looking out for when you, I mean, your mind is going constantly as you're operating that robotic arm. So talk a little bit about your space station experience. I know we had a number of cargo ships come up, and they all require at this point a grappling of the arm and an operator at the other end. Which vehicles did you grapple?
We had HTV-4 arrive.
Again, Japanese do big things big. That's our biggest cargo ship.
Yeah. So I was at the controls to capture that, and we also had orbital demo arrive. So it was the first orbital sciences vehicle. Luca captured that, and I was working with him during that. And I have to say, of all the things I've done in my spaceflight career, when I was at the controls of the arm, and it was just the realization that that vehicle's coming in. There are thousands of people around the world who are counting on nobody but you at that time to successfully capture that vehicle. And I didn't think about it much as I was doing the flying, but as soon as I finished and we confirmed that we had it captured, I could tell my heart was about to come out of my chest. And it just really shows, I mean, a lot of the things you do, you're working more as a team, and you're always working as a team, but for that moment when you're at the controls of that robotic arm, it was me or nobody.
It's all
at that point.
And that's pretty cool. I mean, you can focus through that heart pounding, and you're probably like pushing that aside. I have no idea what that is, but when it's over, the flush of wow, I just did that is pretty rewarding.
Yes, absolutely.
So I would say, so you've operated 4 different arms. We include the OPSS. You have grappled 2 cargo ships. You have grappled a robotic arm, the largest element, pressurized element on the space station. Karen, with all of this experience, and you've worked with so many different other astronauts coordinating these tasks. What would you say was the most rewarding part about your robotics experience, both in space and in training for it?
I think it's the most rewarding thing in all of these robotics activities is similar to the most rewarding thing in everything we're doing when we're traveling in space, is getting the job done and getting a job done well, and working as the team to do that. You know, during the spacewalks, we wouldn't have been able to do the spacewalk activity without the robotic arm help, so I was an important part of the team. Capturing a vehicle, we could not capture the vehicle without the robotic arm, so a very important part of the team.
Well, I'd say that there's very little of the space station that would exist today if it were not for the robotic arms, and especially that big Canadarm2 that we have used to move so many elements of the space station. So I just want to thank you so much for coming on the show today, Karen, because this whole episode is about robotics, and when I heard that that's what our topic was, the first person I thought of was Karen Nyberg. So thank you for being here, and it's been a real pleasure, and we hope to have you back.
Thanks for having me, Tracy. Welcome.
The Canadarm and Japanese robotic arms aren't the only robots we have on the space station. Meet Robonaut. It not only looks like a human, but it's also designed to work like one too. With hands and arms, Robonaut is able to use the same tools that astronauts use. In the future, Robonaut may be used to perform hazardous maintenance tasks or even spacewalks.
Robonaut, a robot meant to work with humans and use human tools. R2's head houses not its brain, but its vision equipment. Behind R2's visor are 4 visible light cameras, 2 to provide stereo vision for the robot and its operators, and 2 auxiliary cameras. A 5th infrared camera is housed in the mouth area for depth perception. Each arm boasts 7 degrees of freedom and the strength to hold 20 pounds in any pose in Earth's gravity. Each arm is approximately 2 feet, 8 inches long, giving R2 a total wingspan of 8 feet. Instead of feet, the robot has clamps that allow it to latch onto and climb up on objects. The legs are also longer than human legs, a span of 9 feet, 2.7 meters, and are more flexible, giving the robot more ways to cling to things inside or outside the station. The advantage of a humanoid design is that Robonaut can take over simple, repetitive, or especially dangerous tasks on places such as the International Space Station. Our experience with R2 on the station will help them understand its capabilities for possible deep space missions.
Welcome back, and thanks for watching this episode of Station Life. Today, we learned about robots. We wouldn't have been able to build our International Space Station without the Canadarm. Good thing for us, spin-offs developed from the technology are helping patients with neurosurgery, and it's now being developed to help those with breast cancer. We're also developing new technologies for robotics in space and on Earth. If we're to succeed with future missions to Mars, we need humans and robots working together. And that's a wrap for this episode of Station Life. So be sure to stay in touch and follow us on Facebook and Twitter for the latest research news. And don't forget to download our Kick a new app for your mobile device. Until next time, stay with us. Off the Earth, for the Earth.
A commercial mission returning cargo from the space station, the first space station spacewalk of the year, and observing a massive volcanic eruption from space. A few of the stories to tell you about this week at NASA. A SpaceX Dragon cargo resupply spacecraft is slated to return to Earth from the International Space Station loaded with more than 4,900 pounds of cargo, including supplies and an array of microgravity scientific experiments. The Dragon's return will cap off SpaceX's 24th commercial resupply services mission for NASA. On January 19th, 2 Russian cosmonauts ventured outside the International Space Station to conduct the station's first spacewalk of the year. During the outing, Anton Shkaplerov and Pyotr Dubrov of Roscosmos performed work to prepare the new pre-shell docking module for future Russian visiting spacecraft. The first docking to pre-shell is targeted for March, with the arrival of 3 cosmonauts aboard a Soyuz spacecraft. Several Earth-observing satellites are helping scientists affiliated with NASA's Disasters Program collect and share data from the massive volcanic eruption that obliterated the small uninhabited South Pacific island known as Hunga Tonga Hunga Ha'apai. Damage assessments are ongoing, but preliminary reports indicate that populated communities in the island nation of Tonga have taken heavy damage from volcanic ash and a tsunami caused by the eruption. Engineers at our Stennis Space Center conducted the first RS-25 engine hot fire test of the new year on January 19th. 4 RS-25s will help power our Space Launch System, or SLS, rocket on future deep space missions, including this year's uncrewed Artemis 1 mission around the Moon. This was the second overall test in the current test series, which began in mid-December. Each test provides valuable data that can be used to help develop the engines. The team assembling our X-59 quiet supersonic technology aircraft is making great progress with the developmental X-plane. The crew successfully added the tail, attached and tested out the positioning of the nose, performed a system check of the ejection seat, and moved the X-59's GE-F414 engine to facilitate a 3D engine scan. This scan helps engineers better understand the F414's fit in the engine bay. The X-59 is being built to conduct research aimed at reducing the loudness of sonic booms that can occur during supersonic flight. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
world is full of new and exciting inventions that continue to push the boundaries of technology forward. Every day, it seems something new is announced, developed, and implemented that changes how humans interact. Just in the past few decades, cell phones, internet speed, medical breakthroughs, and the reinvention of basic infrastructure is beginning to change the norms in our everyday lives. But have you considered how these changes in science, engineering, and medicine occur? To most of us, on the outside of these revolutionary practices, it seems like magic when innovations appear in our lives overnight. In reality, it's years of painstaking work, trial and error, and rigorous testing that occurs before a finished product is ever realized. Researchers in the world of engineering and science move in small incremental steps, slowly building a case for these new revelations until they are sure technologies are ready to be shared with the world. In fact, there is an old saying in research, quote, "An amateur works on a task until they get it right, but a professional works on a task until they can't get it wrong," end quote. Fortunately for all of us, over the past few years, NASA, the FAA, and industry have been engineering the next big idea that may completely change how we interact in our world with the implementation of unmanned aircraft. The idea for inclusion of these aircraft is not new. The basic concept for small flying vehicles has been in popular culture and in the limelight for quite some time. But until recently, these vehicles have rapidly accelerated off the drawing board and into the skies. Over the past few years, NASA has been testing and validating research associated with unmanned aircraft through a project called Unmanned Aircraft System Integration in the National Airspace System, or UAS in the NAS project. This project spanned several years and addressed many of the early concerns of how unmanned aircraft would be integrated into our national airspace. After years of study, the UAS in the NAS project has tackled many of the early concerns. But one last big hurdle remains: to successfully demonstrate how unmanned aircraft will work in harmony within the national airspace. With this in mind, the final phase of testing, called the Systems Integration and Operationalization Demonstration Activity, or SIO, has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has assembled a core strategic group of researchers to analyze and test unmanned aircraft through the SIO demonstration. Some of the key flight activities will include using various sized unmanned aircraft built by 3 different companies to highlight commercial UAS missions that have the potential to provide economic and public benefit to the American people. Throughout the testing, NASA plans to document best practices and lessons learned from the SIO activity and provide it to the UAS community to prepare us for routine commercial unmanned aircraft operations in our communities. On this episode of NASA X, we will take a look back at years of testing and development that have led up to the SIO demonstration flights, and we'll meet the companies that are helping to make these flights happen. This research and engineering has the potential to influence a massive shift in how we receive products and services, and may ultimately make an impact on how people travel and interact in our world. To understand why the NASA team has set up the SIO demonstrations, we first have to look at why integrating unmanned aircraft into the NAS is such a Herculean effort. Here in the United States, we arguably have the best air traffic management system in the entire world. During normal times, around 50,000 flights take off and land daily, with nearly 3 million airline passengers traveling across the more than 29 million square miles that make up the U.S. national airspace system. In that system, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our National Airspace System, or NAS. It has more than 19,000 airports and 600 air traffic control facilities. In all, there are 41,000 NASA operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. With all of this infrastructure, integrating unmanned aircraft systems into the NAS will be demanding, to say the least. But this integration is of vital importance to our country because these new vehicles will be part of the next revolution in national security and defense, emergency management, science, and in commercial applications. For these reasons and more, NASA set out in 2009 to work on several main objectives for the project that included providing research findings that utilized simulation and flight tests, supporting the development and validation of detect and avoid and command and control technologies, and finally, the SIO demonstrations themselves. Two of the biggest challenges that needed solutions before the SIO demonstrations could take place was in the key areas of detect and avoid and command and control. For detect and avoid, one of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. So in addition to instruments, the pilot physically looks out of the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners worked on concepts and designs that allowed safe operation within the national airspace.
What detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means such as radars or cameras to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand.
The second hurdle was with command and control. Because unmanned aircraft are completely different from crewed aircraft, new techniques needed to be developed, including improving the avionics on board the UAS and on the ground. These aircraft must have reliable, safe, and secure data connections at all times while operating in the complex environment of controlled airspace.
Similarly, the command and control part of the UAS and the NAS project is based on the fact that most radio communications that are operated in the airspace now with pilots are voice communication. So it's a pilot talking to an air traffic controller or talking to other pilots, and they use voice to do that. Well, so the aviation spectrum that's been set aside for voice control doesn't work for an electronic control, because if you're going to control the aircraft through some sort of communication methodology, it's got to be done electronically, because you're sending a message to the aircraft to be able to turn or to be able to climb or descend, etc. And so, so the technology that NASA worked on was to develop a radio that could be used in that bandwidth, that spectrum bandwidth, to be able to send electronic messages to and from the vehicle, and thus be able to command the vehicle. So that's why the command and control work that's been done under the UAS and the NAS project is so important.
Over the years, researchers time and time again showed that they had developed the detect and avoid and command and control technology to the point where it could be reliably tested in real-world conditions. Although there were other flight demonstrations throughout this project, the last major hurdle of flying the SIO demonstrations is now at hand. NASA, in partnership with the FAA and industry partners, have begun the demonstrations of potential commercial applications using different sizes of unmanned aircraft systems for the SIO demonstrations. The goal of SIO is to work toward commercial UAS operations in the NAS. In order to accomplish this goal, NASA has partnered with 3 pioneering companies to conduct flight demonstrations in the NAS that emulate commercial missions and begin working toward Federal Aviation Administration, or FAA, type certification.
When NASA was selecting the partners for SIO, we went through a partnership process that included the evaluation of a number of candidate partners. And we were looking for some key aspects that these partners could bring to the table. And so the first was really great domain knowledge in unmanned aircraft and associated technologies. The second attribute was knowledge of certification and the knowledge that's really needed to kind of take these vehicles from the concept and early development stages through to becoming a commercial product. And then the third thing we were looking for are viable commercial missions that would be publicly beneficial. We really wanted to showcase how unmanned aircraft can play a role in the future of the world and have a positive impact. There's 3 different companies that are participating in the SIO activity: Bell, General Atomics, Aeronautical Systems, and AATI. Bell is bringing their AP-70 unmanned aircraft, which weighs approximately 300 pounds and is capable of vertical takeoff and landing and operations around urban areas. The primary mission that they're focused on is emergency medical supply transportation in an urban area. General Atomics is utilizing their Sky Guardian unmanned aircraft for multimodal long-endurance infrastructure inspection. That unmanned aircraft weighs approximately 12,000 pounds, so it's much bigger than the others that are participating in SIO, and is intended for an infrastructure inspection mission at altitudes above 10,000 feet. AATI is using their AI Ranger unmanned aircraft, which weighs approximately 180 pounds, for a pipeline inspection mission at lower altitudes between 1,000 and 5,000 feet. And then lastly, throughout this process, we've been collaborating with the FAA, who has provided extraordinary support and helped us to navigate the regulatory process that's in place for these demonstration activities.
The 3 partner companies are each using various sized and different types of unmanned aircraft configured for the SIO demonstrations.
Over the past several years, actually going back probably a couple decades, NASA's been working on UAS, first more in the technical side and now maybe more on the standard side. And I think the SIO activity was looking, or the objective was to address some of the gaps that still remain. And one of the ways that we were able to do that is by partnering with some companies to go after some of these things. The outcome of the demonstrations is to try to help the companies really get their arms around some of these barriers that still exist, work with the FAA to develop the processes, the solutions to be able to address some of these gaps, and then bring it to a place where the industry can learn off of those lessons. The aircraft that are participating in the SIO activity are really pretty unique, and they span quite a range. You've got airplanes that have propulsion systems that are all electric. You've got a turboprop. Another one is the piston powered. So from a propulsion side, they're pretty distinct. And then even if you look at the way that they just operate, you know, one takes off like a conventional airplane would take off from a commercial airport. Another one can basically launch off of almost anywhere and just land on some clearing. And then another one actually can take off also from anywhere, just vertically, and again landing vertically. So quite a range, even in altitudes, the way that they operate. Some of them were designed to operate at lower altitudes. Some of them were designed to be able to go pretty high, even maybe 40,000 feet.
Each company offers a unique perspective and engineering goal in performing the SIO tests.
So Bell's participation in NASA SIO is really about making sure we get the data that the regulators need to be able to understand not just the aircraft requirements, but the system environments for being able to get advanced aerial mobility actually into commercial space, integrated with the rest of aviation in the national airspace. Bell's actually been doing unmanned aerial vehicles for quite some time. From a commercial standpoint, APT is, a sizable vehicle, a little over 300 pounds, carries 70 pounds of payload. It's critical that we get this right so that we are safe and compliant in the airspace, and that's a part of what NASA SIO is about. They're a trusted data provider for the FAA and other regulators to be able to help us understand what really is required for the aircraft, for the airspace requirements, and then for the integration of those systems together. So NASA's involvement helps drive the technology to a high enough level that we have sufficient data for the FAA to make regulations. I would say the way it's being done right now is innovative. You see, NASA leaning forward with electric and hybrid propulsion, as well as, detect and avoid, and some of the things that we need for the airspace. You see the FAA leaning forward based on their small unmanned experience and knowing that we need to get out in front of this time to make sure that we do it right as we get to larger vehicles. And so that partnership and kind of active arrangement of let's discover together and work together towards what's both safe and economically viable as an overall community is really new.
On this particular mission, the APT-70 was armed from a ground control station, then was instructed to initiate a vertical takeoff. Per its design, it then rotated to fly on its wings, where it was nearly silent to the researchers below. It flew at an altitude of 500 feet above ground level, transitioned in and out of Class B airspace, all while staying in constant communication with the ground station through a redundant data link. On board was the prototype airborne detect and avoid system that provided the remote pilot with awareness of air traffic in the vicinity and recommended flight maneuvers. Initial results were promising, with more validation and testing to continue in the future. Another partner, General Atomics Aeronautical Systems Inc., or GA, flew their Sky Guardian aircraft. It had been used for unmanned missions for many years, totaling more than 6 million flight hours. For this NASA mission, a demo aircraft piloted remotely from California flew for 9 hours from its Gray Butte Flight Operations Facility near Palmdale, California, to Yuma, Arizona. Data was collected from the detect and avoid system to provide situational awareness of air traffic near the Sky Guardian. This system includes a traffic alert and collision avoidance system used in manned aircraft, which fly in civil airspace, and air-to-air radar to detect and track nearby aircraft that may not have active transponders. The particular aircraft in this test may provide services that include hundreds of miles of inspections of rail, power line, communication and canal infrastructure, agriculture monitoring and topological surveys, as well as wildfire and flood monitoring. According to GA CEO Lyndon Blue, quote, GA's work with NASA is opening the eyes of regulators to the safety and utility of unmanned aircraft systems and the performance of certain tasks for public and commercial good, end quote. Researchers believe these types of aircraft will also play an important role during crisis management events, such as wildfire containment. The onboard airborne sensors can see through thick smoke, enabling the craft to inform ground personnel about the location of fire lines so they can deploy resources more efficiently. The SIO demonstration also highlighted how the aircraft can be used for many other civilian and commercial missions as well. The third demonstration flight was a team from American Aerospace Technologies Incorporated, or AATI. Although AATI's craft was considerably smaller than the other test vehicles, its use case was invaluable. It can fly at medium altitudes and carry advanced sensors used to patrol our nation's more than 500,000 miles of midstream pipelines, providing a fundamentally new and unique capability that changes the way we manage health, safety and the environment, respond to disasters, optimize operations, and leverage human capital.
So the mission itself serves multiple purposes. We're proving out the capability of beyond visual line of sight UAS in the national airspace. And the specific applicability for this mission is that we are looking for ways to make critical infrastructure inspection processes safer and more efficient. And so for this specific mission, the Air Ranger took off from our launch and recovery site, and we flew downrange along a oil pipeline which is buried underground, and we performed an inspection of the right-of-way of that pipeline. And we are proving out not only the applicability for critical infrastructure itself, but we're proving out the safety case for actually operating UAS in the NAS, not only utilizing the aircraft's technology for flight, but also utilizing different technologies for safety, such as detect and avoid systems, ADS-B, and flight radar notification systems for having situational awareness of not only what's in the airspace around us, but being able to tell others in the airspace that we're flying as well. In my opinion, to safely regulate and certify these types of aircraft to fly, you have to prove out three different things. You have to prove out that the aircraft itself is mission capable. You have to prove that the aircraft is dynamically capable to change for different conditions. And you also, most importantly, have to prove out the safety case. And so utilizing different types of technology, utilizing different processes and workflows, building the safety case around operating procedures, and integrating all of these different components aside from the actual flight itself, really build the roadmap and really set the stage for the rest of the industry to say, hey, look, this is what the infrastructure looks like. This is what the framework looks like to do this on an operational basis in the future.
Although the SIO demonstrations are now complete, NASA and industry will continue to move forward with exciting new technologies and hardware built on the foundation of successful data collection and testing from the SIO activity. The future of unmanned aircraft is bright. UAS will continue to advance scientific research, benefit environmental protection, assist with disaster mitigation, and move more people and goods to their desired destinations safely and efficiently for decades to come.
This was just the results of a project with a specific goal that we had within NASA Aeronautics, but it's certainly not the end. I mean, integrating UAS into the national airspace is an evolving thing. There are many more challenges. There are many more use cases that the industry is going to come up with. And so we're sensitive to that, and we're keeping an eye on that so that we can really align our research with those areas that are emerging, and hopefully so that we can enable those to really be to come into fruition for the benefit of the American public. And so as we stand up new projects, we'll leverage our experience with UAS and the NAS project, but we'll do it into new areas, whether it's autonomy or other areas of research that will really enable a lot of these use cases and bring about some pretty exciting new markets for the country.
it's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, you know. And I always say, I don't think ever. I think NASA, you know, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. You know, the organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. You know, aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still, it's got better legs today than it did then.
In the beginning, the void, the darkness, then light, then life. And from life came man, joining the caravan for the long, slow journey through a world of discovery, invention, exploration. His marks, his milestones, stretch out through the centuries. His footsteps echo down through the corridors of time. Time. July 1969 in Florida. The footsteps, the caravan quickened. The corridors shortened as man reached outside his world into another void. Today in Florida, they go about their lives, taking only a sideways glance at the reminders of that milestone. Reminders, images that vaguely jog our memory.
This Apollo Saturn launch control is aiming toward a planned liftoff time of 32 minutes past the hour, the start of our launch window on this mission to land men on the moon. The countdown still proceeding very satisfactorily at this time.
Time, it plays tricks on us. It smudges and blurs the sharp edges of reality. But we turn the trick and summon up our own reality, images, sounds, to help us remember.
During the powered flight. The batteries all look good. The next time we go internal will be at the 50-second mark with those batteries, and they will remain, of course, on internal power during the flight. The lunar module, which has been rather inactive during these latter phases of the count, also is going on internal power at this time on the 2 batteries in the ascent stage and the 4 batteries at the descent stage.
They came 1 million of them to this place, drawn by the magnet of history in the making.
The astronauts, the prime crew, were awakened at 4:15 a.m. Eastern Daylight and proceeded to have a physical examination in which they were declared flight ready. They sat down for the normal astronaut fare on launch day. As far as breakfast is concerned, orange juice, steak, scrambled eggs, toast, and coffee. The target for the Apollo 11 astronauts, the moon, at liftoff will be at a distance of 218,096 miles away. The astronauts departed from their crew quarters after checking out their suits. They departed from the crew quarters at 6:27 a.m. and some 27 minutes later, 8 miles away from the crew quarters at the Kennedy Space Center, atop the launch pad at Complex 39, 6:54 a.m., the commander, astronaut Neil Armstrong, was the first to board the spacecraft. He was followed about 5 minutes later by Mike Collins, and finally Buzz Aldrin, the man who's sitting in the middle seat during liftoff, was the 3rd astronaut to come aboard. The weather is certainly go. It's a beautiful morning for a launch to the moon. We expect a temperature of about 85 degrees in the Kennedy Space Center area. We're still go on Apollo 11 at this time. T-minus 25 seconds. 20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Apollo 11, Armstrong, Aldrin, and Collins. They and millions of others reached out and, in their own way, touched another planet. The images remind us that it happened, but not how it really was in the context of the times. George Low, one of the architects of the Apollo program, does remember.
If you think back at the period of the 60s, they weren't very happy years in general. We had well, the ever-deepening involvement in Vietnam. We had riots on the campuses, riots in Watson elsewhere, 3 terrible assassinations. A great deal of strife and turmoil in the country. And yet all of this was overcome by one single event, and that was Apollo 11. The decade ended with it. It was a fantastic adventure that I believe helped overcome all of the bad things of the decade. It represented Americans to ourselves and particularly to the rest of the world as we like to see ourselves and as we hope the rest of the world likes to see us.
The equipment of Apollo, some of it is now in museums, artifacts from an age of discovery. These strange-looking objects, they're there as reminders that after all, it did happen, and it happened the way we remember. The facilities of Apollo, now silent and still. In Houston, Mission Control, the nerve center of manned flight operations. The chapters of space history, first Mercury, then Gemini, then Apollo, were written by the people who sat at these consoles. And these chapters of history came at us with breakneck speed. Christmas Eve, 1968, in the beginning, Apollo 8, the footsteps were quickening. A few months later, Apollo 9. The long years of preparation were contracting into days, hours, minutes. The first manned flight of the lunar module, the Spider. Apollo 10, the dress rehearsal for the real thing. In 5 months, 3 missions, and in the 7th month, the payoff. Then, the celebrations. The images and the sounds fade in our memories, but some things we can't forget. Names: Apollo 11, Armstrong, Aldrin, and Collins. Other names: Grissom, White, and Chaffee. They remind us that it wasn't all success and celebration. There was failure and tragedy. Early in 1967, the 3 crawled into the command module at Cape Kennedy for a test. There was a flash fire. All 3 died. After the shock came the long, painful job of picking up the pieces, learning the lessons, coming together for a common goal. The remains of the launch structure stand as a reminder that the goal was reached. These strange shapes, what do they mean? These towers of steel, what are they? Monuments or leftovers from some earlier age of discovery? In the long history of man, in the slow journey of the caravan, what point do these mark? Historian Arthur Schlesinger. I have no doubt at all that if posterity remembers the 20th century for anything, historians 500 years from now looking at the 20th century, it will be because it will be the century when man first began to break his terrestrial bonds and began the exploration of space. So that's it? As man learned, moved on, and discarded the earlier structures, he came to these. They're marked for further milestones, reserved for future missions, other reaches to other different voids. Historians 5 centuries from now will mark this century, this place, and they will further note that from the void, life, man, it took eons to reach this point. But once there, the centuries and years compressed into days, hours, split seconds of exploration. The wheel, the engine, the airplane, they came slowly at first, then with increasing velocity. And then this, so huge, so powerful, so different that no ordinary modern name would suffice. They reached backward through antiquity to Roman mythology, and they named it Saturn. Saturn. His father was heaven, his mother earth. Complex organization, the mammoth machines, the incredibly detailed technical knowledge, the dedication. It was all harnessed, sharpened to a fine edge, and focused. The program developed and matured. Apollo 17 was launched at night, and even the old hands, the hardened veterans of the space program, couldn't help but feel the awe, wonder, and excitement. In the excitement of the split second of exploration, man doesn't stop to freeze the moment in history, to look at it and ask what it means. He simply lives it out. But in the Apollo program, on their way to the moon, they found a way to live out their strange moments in those strange spacecraft. It may be the peculiar nature of Americans to make history and to have fun in the making. Had fun because we, were confident of success. But the program teaches lessons. Confidence is a transitory thing. Apollo 13.
Hey, Houston, we've had a problem here. Can say again, please. Houston, we've had a problem. Stand by, 13. We're looking at it.
3 days out, barreling toward the moon, an explosion. No one would see the problem for some time, but they went to work on it. The people of Apollo coalesced into a single dedicated unit, linked themselves with their technology, and cheated tragedy. A new chapter in space history was written in Mission Control. Eugene Kranz was the flight director when the problem developed.
Throughout this entire next several days, there was one dominant thought in the minds of all of the flight controllers. We teach them that between God, country, and your own capability, that you can solve any problem that may occur in flight. Throughout the entire course of Apollo 13, there was never any doubt that we'd get the crew back. So there was a very positive approach, and with this kind of approach, you can solve just about any problem that comes up.
Solve any problem, country, capability, old-fashioned words during a time when some said the old-fashioned virtues were forgotten. Well, they weren't forgotten. They were translated into action, into programs which took man soaring above the surface of the moon, away from Earth, but always looking back on it. These divided thoughts, the moon, the Earth, run through the Apollo program a sort of theme. They went there flying in their graceful machines, but they always thought back to where they came from. Perhaps that's natural. The moon is a strange place for men to be flying to. If it's strange for men, for mankind, it's stranger still for the individual man. Harrison Schmitt, Dr. Harrison Schmitt, a geologist, he touched the moon and remembers how it was when Apollo 17 was making its descent, the last flight to the moon, the last time that man walked on its surface. Schmitt remembers how it was.
One's first feelings are a mixture, a very complex mixture of humility, excitement because of something you had planned to do was being accomplished, but of a great attention to detail, to the detail that you had thought about and learned about for so many years prior to the actual event. That detail keeps you occupied with where your hands are and where your feet are, which rung they might be. You try to remember, well, am I at the bottom of the rung? And then as one moves away and tests his way on the surface of the moon and looks around, and in my case, looked around a very magnificent valley, you see a rolling, hilly country that is interspersed with some blocky fields of rocks that you know because you've studied the photographs, and you saw them as you descended surround large craters that have been formed in that rolling countryside. These rolling dark hills merge in the distance a few kilometers away with the very smooth but very bright colored slopes of the massifs. And they rise with a majesty to rocky tops that are almost beyond description because there's nothing like it that we have seen on Earth.
The Sea of Tranquility, Hadley Rill, Taurus Littoral. They were once strange names on the map of the moon, but the men of Apollo gave reality to the names by being there and showing us the places. They explored 60 miles of its surface, and their travels took them to craters, foothills, to explore, to observe, and to sample. The hard rock proof of Apollo, enshrined in the Smithsonian Institution in Washington, D.C., 478.8 grams of microbreccia, under glass for mere earthlings to see and whisper about. Other rocks from the moon, 840 pounds, are being studied and talked about by scientists in laboratories around the world. Not only rocks, tens of thousands of photographs of those strange, exotic features of the moon. And telemetry, data on tape, facts, figures. The studies will go on for years, and the answers will come slowly, answers to questions about the moon and the solar system. The science of Apollo is not merely concerned with samples from past milestones, yesterday's missions. In a special room in Houston, men sit at consoles and command instruments on the moon to send them today's data. and they receive it today within 8 seconds of the command. Science, that's the key, and technology, and something else. In the drama of the moment, few stop to think of the essential element, the one thing that made it happen. People came to this program, government people, university people, contractor people. They brought to Apollo skills and knowledge and determination. This source of human intellectual energy was marshaled, focused, challenged. What came out of the effort was not just a very successful program, but a rich national resource of vast proportions. Crystals from the moon, the symbols of the science of Apollo. Behind it, causing it, was the spirit of Apollo.
I was strolling on the moon one day in a merry, merry month of December. Now, May's the month. May, that's right. May is the year of the month. When, much to my surprise, a pair of bunny eyes. That's the truth. You do that in West Texas and you get around.
We saw something of this spirit. We shared in the adventure, the excitement, the euphoria of being there. We shared it with the men who bounced across the surface of the moon.
Look at the size of that biggie. It is a biggie, isn't it?
And the surprise of discovery. We were there too, all of us, watching, vicarious explorers.
On for the big boulder. Okay, we're headed that way. You get the tongs, John? Yep. I'll carry the rake. Look at the size of that rock. Can't believe it. I can't either. Okay, let's go on back. I am.
And the meaning, the significance of an occasion. That too came to us, flashed into our living rooms on a 19-inch window on the universe.
Countries throughout the world. We hope that this will be a symbol of what our feelings are, what the feelings of the Apollo program are, and a symbol of mankind that we can live in peace and harmony in the future.
There was also pride. They put up the flag and then posed for pictures as any visitor to a foreign place might do. The flag of each mission stood there as a reminder that we had been there, but there was the realization that in truth, it belonged to all the people. There are no boundaries on the moon. The focus was the moon. That's what it was all about. But by reaching up there, we, in a sense, came back here.
As one stands and scans a 360-degree panorama of his own, one of the first objects in the dark lunar sky that you see is a bright and beautiful bluish globe that we call Earth. This globe represented to all of us, I think, not only home, but a very fragile place that we have come back and felt that needed not only protection but understanding.
They first went there in 1969. They last left there in late 1972. Between the beginning and the conclusion, they came to feel, to dimly perceive what it was all about, to come to a perspective on the meaning of it all. Poet Archibald MacLeish has said it better than most. To see the earth as it truly is, small and blue and beautiful, in that eternal silence where it floats, is to see ourselves as riders on the earth together, brothers who know now they are truly brothers. The excitement of the mission, the tension and drama of the splashdown, they remain only in our memories. And in time, they'll be replaced in the future by other missions, other memories. The moments of Apollo may be over, but the understanding and the discovery, they go on. And the full meaning, the real meaning, may yet be in the future too. But for now, for the present, the images and the sounds provide meaning enough to each in his own way and to each in his own time.
I call it the 10% rule. You got to be 10% smarter than the thing you're trying to operate. My name is Greg Cormouche, and I'm here to test rockets. We supply helium, air, nitrogen, and hydrogen so that they can use them while they're testing the rocket engines on the big stands. We have 4 compressors. Each compressor puts out 400 standard cubic feet per minute, and we send that to the test site. I'm a mechanical engineer. I did a lot of mechanical things besides go to college. I mean, I worked on my own cars, heating and air conditioning work. I was familiar with electricity. The first time I walked out on the engine deck and looked at a space shuttle main engine, I said, man, it was overwhelming, you know. Eventually, you know, you stick to it, and I was able to pick it up. The folks that work here are awesome. There's a wonderful group of men and women who keep this place up and running. When you're here as much time as we are, this place is like family. Being a part of the SLS program it's a life event, you know. This is going to be the culmination of all that hard work that everybody put in years ago.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the Space Shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had 2 kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes, and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on shuttle. We've got one engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the ONC building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts within thousandths of an inch to make sure that everything is going together okay.
Putting wiring inside of it, putting tubes for the for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the ONC building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the ONC, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router, it could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt for the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle until splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the Fire Room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load lifting capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punch list items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the 4 corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA, but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process, there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using
Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that will be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspection. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. And so this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spacecraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT-1 flight, as well as the first 2 production flights of the SLS program.
For the SLS PDR, our primary role was the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces, and sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency, as well as the center, that to show people that we are moving in the right direction, to pull together a complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go well from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We've started actually the new design for flame deflector as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench structure, this would possibly be a safety hazard for, our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, support structures. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean room. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module all came in pieces. There's 49 composite panels on the SM. The actual structure itself is aluminum. That's the core skeleton where these composite panels were attached to. After the CM releases and CM returns to Earth, the SM will just burn up with the upper stage of the Delta IV.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent is to simulate similar conditions that the vehicle would experience, say in flight, in launch, and also in landing and recovery.
We usually get the abort motor first, and for this mission the abort motor is inert, meaning a nominal flight.
We're going to have instrumentation on it to again understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
One of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell, it looks the same as what we flew on shuttle. It is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. 2 major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the re-entry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield going final manufacturing at Textron. Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
Avcoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply Avcoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the Avcoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
Hi, I'm Lori. I study the planets, our solar system, and I especially love volcanoes. And this is Ask NASA. The thing I love the most about our solar system is that it's an incredible natural laboratory. We have so many different types of objects in the solar system, from planets and moons and asteroids and comets. We can study each one of those, and they all have something they can tell us about how the solar system formed or how Earth ended up in its special place. And understanding why the other planets are different from Earth actually helps us better understand how we ended up the way we are today. So this is a globe of Mars right here, and many of the reasons why we're so interested in Mars, there's a lot of different processes going on Mars that help us better understand Earth. A lot of the surface of Mars has been preserved for almost 4 billion years, and so we can study a lot of things on Mars that you can't even find on Earth.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So Perseverance rover is going to drive around and find some of the best rocks it can, drill down into the rock and soil and collect those samples so that on our next mission, Mars Sample Return, we'll be able to bring those back and study them in our laboratories here on Earth. There is volcano on Mars. In fact, there's lots of volcanoes on Mars. The largest volcano we know of in our whole solar system is on Mars. It's called Olympus Mons, and it is so giant that the entire chain of Hawaiian Islands could fit inside the crater at the top of that volcano. We see volcanoes really across the solar system on all of our rocky bodies. So on Mercury, we see evidence of lava flows on the surface of Mercury. Even on the moon, we have lava flows that we can see. On Venus, we see the entire surface of Venus is covered with lots of volcanoes and volcanic deposits. Hey! So this is a globe of the moon Io. Io is the moon of Jupiter. That's the most volcanically active body in our solar system. And that's because the pull of Jupiter's gravity on Io as it goes around Jupiter tugs and pulls at Io, and that heats up the inside, and that drives volcanoes. The heat needs to be released. This is the volcano Pele. And there's lava flows down here in the middle, but then there's also this big red-orange deposit, which is actually from explosive eruption of the gases that are falling down onto the surface of Io around the volcano. And it has no atmosphere, so if you were to turn it like this and look at this volcano from the side, you see a big umbrella of gas. The particles just come out and then they drop back down. And I started studying volcanoes on Earth about 35 years ago, and then started studying volcanoes on other planets, and that grew into my love of our solar system. So the asteroid belt really contains a lot of leftover material from solar system formation. You can imagine that when the solar system first formed, the particles kind of came together and made bigger particles. Some of those came together and created the planets. We actually find asteroids in lots of different parts of our solar system. We have asteroids that are near Jupiter, the Lucy mission, which is going to launch this year in 2021, and it's going to go study those special asteroids that are trapped in Jupiter's orbit. And then next year we have another mission called Psyche that's going to a particular asteroid called Psyche that looks to be made mostly of metal, of iron. It may actually be the exposed core of a small planet that may have had its crust blown off by an impact and left that metal core that we can see. There is definitely water on the moon. We know this because we've observed with some of our orbiters being able to identify that there's water molecules on the moon. And in fact, some of these we believe are preserved as water ice, perhaps in these permanently shadowed regions that are very, very cold near the poles. And what we need to do next is to actually go down to the surface of the moon and actually look at that ice up close. And so that's what we're doing with the Artemis mission. We'll be focused on looking for some of that water in the soil of the moon. We have explored really the far reaches of our solar system. We have sent missions to Mercury near the sun and visited all of the planets in our solar system, all the way out even to Pluto. And then one of our missions called Voyager actually has 2 spacecraft that have now even gone beyond the edges of our solar system. So we have really explored the whole expanse of our solar system.
Cool. Io and Mars are great.
Let's try it again.
Oh, that's too high. That was a fastball. She had a fastball.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Station, this is Houston. Are you ready for the event?
Station is ready.
Telangana today. This is Mission Control Houston. Please call station for a voice check.
Station, this is Nambita Srivastava with Telangana today. How do you hear me?
I've got you loud and clear.
Hello, hi Raja. This is Nambita from Telangana today. How are you doing?
I'm doing great, Namrata. Great to hear from you. And happy to be talking to you from the ISS as part of Expedition 66.
It must have been incredible going up there. I remember the last time we spoke, you told me it was a dream from when you were a kid. How does it feel being an astronaut?
Well, it's been a great experience. I think, once the second stage cut off on the Dragon and we were in orbit, it was just a dream come true, and then actually getting onto the space station and getting to live here has been amazing. We all actually on our crew remember the first time we saw the ISS from the Dragon about 40 kilometers away as we were coming up in a day pass, transitioning from night to day, and the sun had hit the station, and we could actually see it, and it looked just golden, and it was pretty amazing. And it's been a blessing to be up here and getting to do science every day and work for the people on Earth.
That's incredible. Speaking of the science that you've been doing on ISS, if you can please enlighten us on what are you working on there?
So we just sent home a cargo Dragon that had a whole bunch of science that has to be analyzed on the ground. Some of that I've been doing personally a lot of plant science lately. So on what came down on Dragon was a bunch of plant shoots and roots, and they're doing some cellular analysis of that. Just this week, I set up an experiment called Ponds, which is basically looking at different root systems, so different ways of watering the plants to look at different methods to irrigate. And then another set of research we're doing has to do with, it's almost like stem cells of cotton plants. And so we're trying to make cotton more drought resistant. And we can do the genetic mutations a lot faster here in microgravity and culture the stem cells into much bigger collections than you can on Earth. And so that's just some of the plant research that's been going on this week.
That's amazing. And you're the commander of the mission, Raja. What are your responsibilities? What are the day-to-day things that you people engage in?
So as part of the Crew 3 part, as part of the Dragon, basically our job is to keep the vehicle healthy, so we check on it from time to time. That's eventually going to be our ride home, and so we maintain our readiness and vehicle knowledge. But most of our days are spent on the station doing science, and there's kind of three, science and maintenance. And so there's kind of three categories of things we do on a day-to-day basis, and they kind of change every day. One is like science on ourselves, so we're the subjects. So whether that's blood, bone, cell, DNA, all kinds of studies on ourselves. Then there's science on other things, what I call fundamental research science, like the plant science. We're doing a bunch of combustion science experiments. So there's about 300 experiments that we're doing while we're up here during our 6 months. And then the third part is maintenance. And so the station's been continuously operated for over 20 years. And so just like a 20-year-old house, there's plenty of things to fix. And so a good chunk of our time is spent preventatively trying to fix those things. Or in some cases, they break and we fix them after they break. And in some cases, we go outside the station and fix it in the form of spacewalks.
Right. So, and being there up in the sky, how is it that you? I mean, I'm sure you must be seeing all the sunrises and the sunsets and everything. How is that experience?
Can you say that again? You cut off halfway through it.
I was asking about all the sunsets and sunrises. I noticed that there was a Facebook post about how many sunrises you saw on the New Year's Eve. How has that been? Incredible views from ISS.
God, that's been amazing. So yeah, our orbit's about 90 minutes to get around the Earth. So we see a sunrise or sunset about every 45 minutes, and yeah, it's pretty fantastic. When the sun comes up or it goes down, you wind up seeing the atmosphere of the Earth sort of edge on. It gets back illuminated, and I think to me the most incredible thing is seeing how thin the atmosphere is compared to the Earth and to the space around it, and realizing that everything we know and understand and love and do as humans is in that one little, really just looks like a razor thin layer of air. And so it's amazing. And then the other thing is you have to be careful not watching the sunrise when it gets too close to bedtime, because watching the sunrise and then trying to go to bed can be a little difficult.
Oh, all right. And how is your body adapting to the new environment? Are there any changes that you have noticed?
Yeah, so definitely it takes some time to adjust. There's both physical changes. So when you first get to space, you tend to shed water out of your body because the blood and fluid shifts up in your body, and so your body's reaction is to get rid of that. And then there's also some mental changes. So what I found is the first few days, it's very hard to multitask. And part of that is just you're almost like a baby. You can't feed yourself. You can't drink, you can't go to the bathroom on your own, you need help with just about everything. And so where on the ground you can put something down and come back to it. Gravity is a great organizational tool where you can walk away from something, and so it's you really have to think in space, and it takes a while for your brain to adapt. And then I also think just understanding spatially that you can use all the surfaces. So, obviously we can work on the walls, the ceilings. When you first get here, it takes a while to realize you can do that, and it's somewhat uncomfortable. You always want to make the ground or towards the earth up. But after a while, you get very comfortable just working on whatever surface you find, putting your feet wherever you need to, and reorienting and doing your work, which allows us to have 4 times the usable surface area and workspace that you would on the Earth.
Right. But what has been the hardest thing to do?
I think the hardest thing to do for me in space is learn how to stop and start quickly. So early on, you don't really have a sense of your own momentum, and so when you start moving down, like for example, if I were to start coming towards the camera and then have to stop early on, I would probably crash into the camera. So it takes a while to anticipate how much force you need to start, which is very little, because if you put too much force in starting, it's really hard to stop.
Right. Right. And how does your family feel about you being up in space for 6 months? What does the kids think?
Well, so fortunately, NASA and the folks at Johnson do a great job keeping us connected. So we have, I'm able to talk to them pretty regularly, my family over the phone, over essentially an internet phone, and then I'm also able to see them about weekly, essentially via like a Skype or a FaceTime video call. So we're able to stay pretty well connected. Obviously, I'd rather be with them in person, and they'd rather have me there. But I think my wife is definitely used to this, being a military spouse, and being used to me being deployed and gone. This is kind of a new experience for our children, but I think they're very excited about it, and they are happy to be supporting basically the people of Earth.
Right. Any message for the young people who are looking up to you and want to become an astronaut?
Yeah, I think find something you're passionate about and do it, and enjoy doing it. There are plenty of challenges ahead of us. ISRO obviously looking to launch their first crewed mission in 2023. So the Indian youth have plenty to be involved in and get excited about, and the world has plenty of problems ahead of us to solve to be able to go to Mars. So we're going as part of the Artemis program to the moon to stay and use the moon as a test bed to get to Mars. And whether it's long-term travel and human experiences after years in space, whether it's radiation shielding, whether it's propulsion, there are so many engineering challenges to solve. And so I think what I'd ask the youth is to get passionate about something and help us solve those problems and get to moon, the Mars, and beyond.
Great. Thank you so much. Thanks a lot, Raja, for connecting to us, and all the very best for all the future endeavors from us.
Thanks very much, Nabra. Take care, and bye to the people of India.
Station, this is Houston ACR. That concludes the Telangana Today portion of the event. Please stand by for a voice check from KWWL-TV.
Station, this is Daniel Perot with KWWL-TV in Waterloo. How do you hear me?
Hey, Daniel, I've got you loud and clear. Good to be with you today.
We appreciate you taking a couple minutes to talk to us. You've been up there for a couple weeks. What is life like up there on the International Space Station for you?
It's been great. I think my favorite part about it is every day is different, and you actually don't even kind of know what you're doing the next day until the night before. So our schedule's put together by the ground team at Johnson Space Center, who's always trying to balance priorities of science, things that need to get fixed, preventative maintenance, and all the science we have to pack in. So about 300 experiments during the time we're here, and so it's always cool to, right before you go to bed, take a look at the schedule the next day and see what you're slated for. And so I think for me that's been the best part is having every day be at a kind of a surprise to wake up to, and at the end of the day knowing having a great feeling about what you got done.
What has been the biggest adjustment for you over the last couple weeks as you've gotten used to living up on the International Space Station?
I think at this point I know enough to be dangerous. So the first few weeks, I think for me, it took my brain about 2 weeks to sort of adjust. I think for me, the biggest adjustment was just the orientation of things. And so it's very natural. When we train, we have simulators on the ground that look like the space station, and we get so used to doing everything standing on the floor. But in space, obviously, you can use any surface as the floor. And so it takes a while to get used to that. And so whether, if I had to open this locker, the first week or two, I might be really tempted to stand on the floor and do it, but then you realize, well, it's actually a lot more efficient to just put your feet somewhere else and get more leverage. And so just getting used to that, or where to put your feet, and where to move around as you're accessing different boxes or tools or cables, and getting comfortable with that is probably the hardest thing to get used to. And once your brain understands that, you can be a lot more efficient and not run into anything. So probably the first week I was here, I left a trail of destruction behind me. As you can see, there's cables and lines running everywhere, connecting all the different experiments as we move things in and out or upgrade equipment. And so as we float through the modules, it's really easy to snag your foot under a cable and pull it out without even knowing you're doing it. And so adjusting to that and realizing that your body is floating all around you as you move takes some time to get used to.
Where were you when you found out that you were going to space, and what has the experience been like? Has it so far been like what you expected it to be?
So where I was actually at the time when I was working on the Demo 2 mission, which was the test mission where Bob and Doug flew the first Crew Dragon up to the space station. And so I was part of the team that was helping work on the commercial crew program to get both Boeing and SpaceX back putting U.S. astronauts into space. And so at the time, that's where I was, and it's been everything I thought it'd be and more up here. And getting to fly on a vehicle that I got to help work on and see as part, as part of the testing phase, it was even a bigger thrill.
What did you do to prepare yourself for this 6-month stay on the space station?
So actually, I've probably been preparing all my life in some sense, whether it was being used to being away from the family or, preparing mentally for that, learning, about engineering and having sort of a working knowledge of the systems we work on, a love of science that I've had since I was a kid, and just the idea of discovery. In terms of, the specifics of NASA, I showed up about 2017, and so about 2 years of what we call basic training, or ASCAN, which is a broad general training to be able to work on the ISS. And then once you're mission assigned, you spend about 18 months focusing on that specific mission and the vehicle that you're going to use to get to space. And so all told, it's about 3.5 to 4 years of training for the increment of science that you do up here on the space station.
What does your family think of you being up on the space station for 6 months? Do you get to talk to them often?
I do, yeah. So through the wonders of technology, the same satellites that we use to downlink data and the payload information that the scientists use, we also can use to make internet phone calls to our family. And then about once a week, we have the ability to do a video phone call with them as well. So we're able to stay pretty well connected. Obviously, especially as a father with young kids, I'm missing a lot, and that is hard for me and hard for them. But I think both they and I realize it's definitely for the good of a lot more people than just us. And I think, very similar to military families, we actually have it a lot easier up here. Everyone's trying to take care of us compared to the people who are gone 6 months to a year for the military to places where people don't want to take care of them or try to hurt them. So, in that sense, we have it very well, and lots of people taking care of us, lots of support for them on the ground, and lots of support for us here up in space. So we're very blessed, and I'd rather see them every day, but I think every one of us realizes that we're doing a lot more and making a lot more contributions to the general population by giving up a few months up here.
Tell me about some of the projects that you're working on the International Space Station during the day there.
So there's about 300 that we're working on already up here. We just sent a bunch home in the Cargo Dragon, and the Cargo Dragon is unique. It actually lands, and they're able to then pull that science out of it and do more ground analysis. This past week we've been doing, or personally I've been doing some combustion research, and so as you can imagine, fire in space can be a problem. You want to make sure that if you're studying fire, you keep it very contained, and so the research has to do with both what's called cold flames and then also lower emission flames. So trying to find a way to have less carbon emissions of combustion, which would obviously have huge implications on Earth. Also, I've been helping this week with some CO2 scrubbing technology demos, and so we have 2 of those going on, which again, clearly if we could reduce carbon dioxide levels, that's a huge benefit to the population. And then also a bunch of plant research, and so we sent down on Cargo Dragon some shoots, plant shoots and plant roots that we had harvested up here that they'll analyze at the cellular level. And then the 2 experiments just started this week, one looking at different root growth systems and different methods of getting water and nutrients to plants in space. Right now it's pretty resource intensive from a time standpoint because it doesn't naturally come out of the ground like it does on Earth, and so there's some new technologies we're testing out to see if we can make that a little easier. And then also what roughly equivalent to stem cell but for plants research, and so it's cotton stem cell cultures that in space can get really big. On the Earth, because of gravity, those collapse and they break apart, but in space where there's no gravity, you can get really large cultures, and so we can do some really quick genetic analysis of these modifications, and they're trying to find better drought-resistant crop strains.
You grew up here in Eastern Iowa, grew up in Cedar Falls, went to school here in Waterloo. So how has that shaped your professional journey, and what would you say to a student who is sitting in a Waterloo high school classroom today?
So I think it was a huge part of who I am and who my wife is, who's also from Cedar Falls. So I went, had the benefit of growing up in a town and going to a school where the teachers cared about you as a person. You weren't just a number, and I think that was true of the whole Cedar Falls, Waterloo area. There was a really individualized attention, and that was something that I think made a big difference. And throughout your professional career, we talk a lot about having mentors and people like that. But in retrospect, I had mentors even as a child, and that was something that was hugely important. And I think what I would tell the people of Eastern Iowa is, it's been great to see Iowa from space. Definitely enjoy the snow, and it's been cool to see the snow line move south as we've made passes over Iowa. But yeah, keep doing great things there in Iowa, and I appreciate all the time and energy people spent and put into raising me there and making us better people. And I think my Midwest upbringing is a big reason why my wife and I are doing the things we do now.
You mentioned the Artemis program. Do you hope to go to the moon or maybe even Mars one day?
I'd love to. I think it's going to be the people watching, the high school students and the grade school students that are going to go there. I think the cool thing about the Artemis program is when we go back to the moon this time, we're going there to stay. And so it's not just a mission or 2 that we're talking about, but we're talking about establishing a long-term presence. And so the high school and grade school students that are growing up to be engineers and scientists are going to be the ones that solve the problems that take us from the moon to Mars and beyond. And so I'd love to be a part of that. There's an Artemis development organization within NASA already looking at everything from the booster to get us there to the capsule to get us from Earth orbit to the moon, the gateway around the moon, the lander to get from the gateway down to the moon. So metal is being bent, there's systems being tested. SLS is flying this year on the uncrewed mission, so things are happening really fast, and it's pretty cool to be a part of all this and being in on the testing and development of these systems.
Well, thank you so much for your time today. We appreciate you spending a couple minutes to talk to us today.
Daniel, thanks to you guys. And like I said, stay warm there in Iowa. I know it's been chilly lately is what my mom's been telling me.
We'll do our very best.